Thanks for having me. And this tutorial is about the causality. Essentially, in this part, you will see some basic concepts related to causality, how we can discover causal information or causal structure or even causal model from observational data or non-experimental data, sometimes known as causal discovery, and how we can infer the causal effect of some variable on some other variable, sometimes known as causal inference or identification of causal effects. And finally, you will also see some connection between causality or causal modeling or causal understanding and machine learning. So you'll see how we can leverage causal understanding to solve some of the machine learning problems. So if you have any questions, please immediately let us know. I would like the tutorial to be more interactive. Okay, now let's start. So here, let's start with some well-known problems in machine learning or artificial intelligence. Right here, you can see an example. In 2015, Google released Google Photos application. It's used for photo categorization. So right here, you can see, oh, this is airplane, it's car, bike, and so on. And unfortunately, you can see right here, this is a huge mistake because African Americans were labeled as gorillas. So this is a big issue. For human beings, right, it's very easy. We can easily do classification in this case. But for machines, it seemed to be very difficult. Actually, after 2.5 years, Google solved the problem. So you can guess how they solved the problem. Give it a try. So essentially, finally, after such a long time, Google just removed the label gorilla from the label set. Now nothing will be classified as a gorilla. You know, gorillas cannot complain. That's why it's a solution, right? But from this example, you can see why, or you can see the difference between machine learning and human learning. Something is very easy, right? This, in particular, this task is very easy for us, but it's very difficult for machines, although we have advanced statistics and machine learning techniques. And right here, you can see another similar example. Here you can see the picture, right? You know it's panda. And then after you add noise in some specific way to the picture, and all of a sudden, the machine will classify this image as something different. And for us, for human beings, clearly it's the same thing. So what happened? Why do we have this issue, right? So essentially, generally speaking, we have this observation. We human beings have our own decision process, right? A way to make decisions. And machines also have a way to make decisions. We have input, right? We process the data and then we give the decision. As long as the two decision processes, one for human being, the other for the machine, are different, then we can have this issue. We can just tune or change the input in some specific way to change the output of one of them, only one of them. So right here, you can see, oh, we just change the input in some way, and then our decision is the same, but the machine's decision is totally different, right? So we have this adversarial attack problem. So how can we solve the problem? Clearly, we have to design the machine's decision process, right? We have to change it so that it's consistent with our process in some way. And what process do we have? We have causal understanding, we have generative modeling. We see the whole world and we want to find a model for the world. And then we make a decision based on our understandings. Right here, right? We extract different features and we make a decision based on the features, those features, interpretable features, but not, machines do not make decisions this way, right? I have raw input, I directly calculate something from the raw input, then I'll give a decision. So you can see the difference. And then what do we mean by artificial intelligence? Right now, I can give some, we can just see some phenomena associated with artificial intelligence. First of all, traditional machine learning usually assumes a fixed distribution of the data. That's why you can train something right here on the training data and then apply the learning machine you trained, right? Or you obtained from the training data somewhere else. So this is because you believe they have the same distribution. And the classical problem in machine learning is to avoid overfitting, right? However, you can see a lot of problems cannot be understood this way. Right here, if you play, say, tennis very well, then you can easily learn to play other things, and you can easily play them very well. We know how to transfer, we know how to decompose very complicated things into small modules, and we know how to transfer those things to new tasks. And right here, to the right, you can see as a human driver, even if the scenario is totally different from what you observed before, you can still understand it. You see the connection between this scenario and the previous ones, and then still you can make right decision, right? But for machines, it's so difficult. Why? Because we know if it's a non-parametric system, then given that they support the test data point, new data point, is not contained in the support of the training data, then basically you don't have a guarantee, right? Anything can happen. Then what do we mean by intelligence? So first of all, we know if we are intelligent, then we are able to understand what's going on. We have the ability to understand the environment. Of course, here I don't give a definition of understanding, but basically, we know if something is intelligent, then intelligence should have the ability to understand what's going on. Later, we will have a better definition of understanding. And because of the understanding, we can do control or intervention in some specific way to achieve our goal. We can decompose very complex things into simpler, small things, right? Modules. And then we can just combine different modules, small modules, to build a big thing, to have a big picture, known as information fusion. And we can do learning with few examples by making use of our experience, right? And we can do not only interpolation, but also extrapolation, right? We can go beyond the experience because we can understand the relationship. We know, oh, even if the distribution is different, we know something can still apply, right? So for machines, this is very difficult. And we just saw what intelligence or what artificial intelligence could do. How can we really achieve artificial intelligence, right? Well, some people may say, oh yeah, we can just study how the brain works, and then we can just construct something to completely mimic that. Then this is the typical machine learning way to achieve artificial intelligence, right? Given a particular data set, you want to construct something optimal for that data set, but it's not general. So let's try to have a general understanding of intelligence. Let's use the evolution, selection, and growth perspective. So we define intelligence because we survive, we prosper, then we think we are intelligent, then we want to find something to characterize this particular property, right? So first of all, we survive, right? And we prosper. That means we have the good, we can make good prediction and decision across different scenarios, across all scenarios. And statistically speaking, to do this, we have to form some inner compact representation of the external world. This way we have a simple model, right, for everything, and we know how different things are related, then we can make good prediction. We can leverage information from other places, right? And furthermore, we are creative. We can change the world. We can just build new things, right? So creativity relies on causal representations of the world. Right here, we have the two abilities, and they are related. They are somehow consistent. When we were very young, right, we couldn't really do interventions. And by observing and thinking, we could form some kind of representations. And later, we can do manipulations. We can verify a lot of things. And there does not seem to be a huge gap between the two types of representations. So now, the first thing is about prediction, and the second thing is about causality. Because they are somehow consistent, and now we can try to solve the following problems. First, how can I analyze data without doing manipulation to find the causal information? This is the causal discovery. Second, suppose I have a causal representation or causal understanding, how can I make use of such information or such knowledge to make good prediction across scenarios? This is something like transfer learning, right? So essentially, in this tutorial, you will see how we can do causal discovery and how we can leverage causal information to solve other problems. Questions? If you have any questions, please immediately let us know. Okay, so we know that we have to distinguish between causality and association. In data, we can easily discover association, right? But causality is clearly more important in most situations. Here you can see some examples, but this is the news report from the Telegraph. And it says couples who share the housework are more likely to divorce. Okay, this sounds horrible, right? So that's why it's not surprising that people had a lot of follow-up discussions. For instance, here, right here you can see, does sharing housework really lead to divorce? So for us, we want to get some information as to what we can do to make things better, right? That means we really want to find a causal understanding of the phenomenon. Right here, we use the word lead to, so this is the causal. We want to find the causes. We want to see whether this relationship is causal or not. And without the causal understanding, we cannot really change the environment properly. Okay, so what's causality? What's the dependence? We know that it's very famous. This statement is very famous. It says causation implies correlation, but the correlation doesn't imply causation, right? So here, basically we can say, yeah, that's true. However, maybe it's better or it's more fair to say that causation implies correlation, but the correlation doesn't directly imply causation. Under some assumptions, or if you have additional information, then immediately you can find the causation from correlation or dependence. When I was very young, I used to think that correlation implies causation, right? It's not surprising. And then after taking some statistics classes, I changed my mind. Most people did that. And then after doing research in the field for some time, now I'm very optimistic. Basically, we can say that in almost all situations, with rather weak assumptions, we can really discover causal information from various kinds of observational data. Sometimes we have IID data, sometimes we have time series, sometimes we have non-stationary data, and so on. But in all cases, we can discover causal information under the suitable assumptions. So we say two variables are associated if and only if they are dependent. As you can see from here, on the left, you can see the definition of dependence. Now, we say they're dependent if and only if different values of one variable correspond to different distributions of the other variable. Meaning that if I want to model or predict the other variable, say y, then x would be useful, right? And when we say x is the cause of y, we mean the following thing. We have a particular way to change the system. In particular, we want to change x, only x. Then after you change x, if you observe a change in the distribution y, then we say x causes y. And here by change, I actually mean intervention, intervene on this variable. So what does it mean by intervention? Essentially, when you want to intervene on x, you have to guarantee that at least for the moment, no other variable is changed by this intervention. You only change x. And then if you guarantee that, I only change x, now I observe a change in y, then there must be a way for x to change y. In other words, x is the cause of y. Okay, so of course, this definition of causality is a kind of circular, right? Because if you have no idea about the causality, how can you make sure this is the right intervention? How can you be sure that, no other variable is changed by this particular action, right? But circular definition can still be very useful. So how can we find the causality? A traditional way to find the causality is to do manipulation or intervention. So, here you can consider some examples. Or you can think of causality from this perspective, or you can verify whether variables are causally related by by imagine how intervention, or the effect of interventions. So right here in the first example, we have very hot weather, right? And we have high sales of ice cream. So in this case, if there are causal relationship between the two events or variables, you can consider them as binary random variables. So you can see, oh, yes, I can do intervention. So here I can, if I can find a way to make it very hot, right? Then a lot of people will buy ice cream. It's very natural. However, I can find a way to increase the sales of ice cream. Say, I can just hire a lot of people to buy ice cream. This is the intervention because this action will not directly change the other variable. But then you can see, oh, this action or the high sales of ice cream will not make the weather hot. That's why we can see, oh, the first event causes the second one, but not the other way around. And then let's look at a second example right here on the right. Here we have one event, which is a bus coming. And right here, the second event said that the guy is leaving home. Suppose this guy go to work by bus every day, every work day. So around 8:30, this guy is leaving home and the bus is coming. So the two things are clearly correlated, related, right? They are dependent. Now, do you think there is a direct causal relationship between the two events? They are related, right? So you can think of, just think of the causal relationship. Now, intuitively, yeah, there might be a causal relationship between them. Then it's very surprising because there's no physical way for them to be related, right? How can I have a causal relationship between them? Then let's look at a problem from the intervention perspective. So suppose the bus is coming. Now I want to do intervention. For instance, I can just jump in front of the bus. Hopefully the bus will, that's very bad, but the bus will stop, right? This action will not change this guy's behavior directly. Now you can see the bus stops and that guy will still leave home as usual. That means the bus coming is not a cause of the guy leaving home. And similarly, suppose the guy is about to leave home. I just suddenly close the door, right? The guy will stay home and you can see the bus will still come as usual. Now you can see there are no direct causal relationship between the two events, but they are dependent. Why? It's because we have some common cause, right? In most cities, we have timetable, and timetable is a common cause of two different events. And of course, you can say, oh, now I want to change the second event right here. Maybe I can just change the timetable, right? That's a change. However, that's not an intervention because if you change timetable, then the other variable or the other event will also be changed by the action. That's why it's not an intervention. So in order to verify that it's really causal, you have to guarantee that your action is an intervention. Otherwise, things can be very complicated. However, now you can see, given that it's really hard to apply interventions, how can we really discover causal information in reality? So we have to make use of a lot of information. Sometimes we have temporal information because in most cases, causes happen before effects. And we have, we have understanding of some very simple causal mechanisms, and then we can combine the causal mechanism to understand complex systems to have causal information, right? And sometimes we can really discover causal information by observing and analyzing the data. So typically there are three types of problems in artificial intelligence. Right here, let's just have a quick look at the problems. The first one is known as prediction. So here I have data, I have three variables, x1, 2, 3, I have data. Now I want to see, answer the following question. Would the person cough if we find he or she has yellow fingers? So here x1 denotes smoking, x2 yellow fingers, and x3 whether the person coughs. Okay. So now you can see this is just a prediction problem. And this relies on this conditional distribution of x3 given x2. You can use linear regression, logistic regression, deep networks to derive essential features of this conditional distribution to make a prediction. Right here, only the observed data, right, are needed. You can just directly find something of this conditional distribution. The second type of questions is about intervention. So you want to see the effects of interventions. And clearly, this is the causal problem. And sometimes intervention is also known as manipulation. So typical questions are like this one. Would the person cough if we make sure that he or she has yellow fingers? So we do intervention, right? We just make sure the finger color is yellow. And then we want to see whether a person cough. Now you can see the probability distribution of x3 given intervention x2. And this is known as interventional distribution. And to do so, clearly we have to make use of causal picture. And the third one is more detailed, is known as counterfactual reasoning or counterfactual inference. So the question is as follows. Would George, a particular person, cough had he had yellow fingers, given that he does not have yellow fingers and coughs? Now you can see compared to the second question, we have this condition. We observe something. Right here, we observe that George does not have yellow fingers and coughs. So we can just write down this, formulate this problem this way. We want to say something about x3 after we do intervention x2. Right here, this is intervention, given this condition we observe. And this is counterfactual because we already see something about George. George does not have yellow fingers and George coughs. Now we want to do something that is not realistic, right? We know this is going on, and we want to see what if something had been different. What if George had had yellow fingers? So this is known as the counterfactual because you are doing something like reflection. You want to reflect something that already happened, and then suppose you can change something. You want to see the effect of that change, that relative to this particular unit you are talking about. So here in this example, we are talking about George, a particular person. Okay. So this is the outline of this tutorial. So essentially, we have 4 parts. First, we'll see what we can benefit from causal thinking. And I will give a brief introduction to graphical models because we use a graph to represent the causal relations. And then in the second part, we'll see how we can learn causality. In particular, we will see how we can make use of the so-called constraint-based methods for causal discovery. And we'll also see how we can consider practical issues by developing extensions of classical methods, constraint-based methods for causal discovery. Here by constraint, I mean conditional independence constraint. Later you'll see why we use this name. And then the next part, we'll see how linear non-Gaussian method or nonlinear method can be derived for causal discovery. So here we make use of additional assumptions of the causal mechanism, and then as a consequence, we can learn more information about the causal structure. And also we'll see how we can extend those methods to deal with practical issues. And then we'll have a very quick look at how to identify causal effects of some variable on some other variable. And finally, we'll see how we can leverage causality in solving machine learning problems, including domain adaptation and image-to-image translation. Causal thinking. So here I will give 3 examples to illustrate what we can benefit from causal thinking. First, this example was used by Fisher in the 1950s. Here, smoking is a common cause of yellow fingers and lung cancer or lung disease. And now you can see it's not surprising that yellow fingers and lung cancer are dependent. However, if you want to change the incidence of lung cancer in a particular area, what can we do? We cannot just change the color of the fingers, right? We have to go to the cause. We have to change smoking variable. So now you can see, if you want to change something, you have to care about the causality. If you just want to make passive prediction, yes, dependence would be enough in a classical IID setting that you will see. In some other scenarios, to make a prediction in complex situations, sometimes we still need the causal information. Okay, this is about the difference between dependence and causality. And the second example is about confounding. The third example is about the selection. This is the second example. So this was a real data set here. So it's about the patients with kidney stones. So we have two groups of patients. One of them has small stones and the other has large stones, this row and that row. And we have two treatments, A and B. Now you can see, as you can see from the table, no matter which group you are considering, treatment A is better, right? Right here, for small stones, the recovery rate, this number is the recovery rate, is 93% versus 87%. So A is better. And for the group with large stones, the same thing happens because treatment A has a recovery rate 73%, which is higher than 69%, right? And now, if you combine the data, just consider the whole data set, you can see, oh, treatment A has a recovery rate 78%, and B has 83%. B is better. So now comes the question. Suppose now you are a doctor, and suppose you only care about the recovery rate, means that you just want to maximize the chance of recovery. And now, suppose the new patient just come to you. Would you recommend A or B? Right? You may say A, yeah, if I know the stone is small, I will recommend A. If I know the stone is large, I will recommend A. If I don't know that, I will recommend B. That's why we say it's a paradox. Clearly, the stone is either small or large. You will recommend either A or A, and finally recommend B. That's the problem, right? So why do we have this issue? This is because the stone size is actually a common cause for treatment and recovery. And when we do when you make recommendations, you only care about this link, called link, from treatment to recovery. You don't care about the stone size. You care about this effect. However, because of the existence of stone size as a common cause for treatment and recovery, the dependence pattern in particular, the correlation between treatment and recovery can be rather arbitrary. This correlation does not reflect the information of the causal influence, does not really reflect the causal effect at all because of this common cause. That's the problem. So right here you can see another example from Pearl's book. So here X and Y are the exercise and the collateral respectively. And you can see right here we have different age groups, 10, 20, 30, and so on. So you can see for each age group, the more exercise you do, the less collateral you are going to have on average. That's very good. That means, we should do more exercise to reduce collateral. However, if you ignore the age information, now you can see collateral and exercise are positively correlated. Same that, the more exercise you do, the more collateral you are going to have. That's horrible. And we have this phenomenon because we just ignore the common cause, which is the age right here. And when you do recommendation, you only care about the causal effect, not correlation. Okay. Now let's consider the third example. So let's go back 50 years. Now probably you would find that female college students are smarter than male students on average. Why? We believe that overall, females and males are kind of equally smart, right? In some way. So why do we have this phenomenon? Someone is speaking? No?
No.
Okay, thank you. So why do we have this phenomenon? Basically, this is a selection problem. At that time, it's rather difficult for females to be admitted to college. Right here, you can see gender and IQ are both causes of being admitted. And although they were originally independent, gender and IQ were originally independent, given the common effect, usually they are not independent anymore. They are dependent. So to give a very concrete example, just think of college as the sum of gender and IQ. If I know the sum, then the two variables will not be correlated, will not be independent, right? The larger this guy, the smaller this guy on average, because I know the sum. So this is a particular type of dependence introduced by selection phenomenon. Okay, here you can see another example. Right here, you can see a lot of holes in the airplanes that return from walls, right? Now let's try to answer the following question. Suppose you want to make the airplane better by putting some armors somewhere on the airplane. So would you like to put the armors here or here? Right? Some people may say, oh, here you can see a lot of holes. That's why we should put armor there to make this part stronger. So here, clearly, we have to make use of the process. This is the process being hit, the airplane. One variable, the other variable is where it got hit. And then both of them are causes of survival, right? So airplanes came back, that's why they survived. And then we observe the probability distribution of B and W in hit and where given the airplane survived, right? We just see the holes in the airplanes that came back from wars. And then, in order to put armor in the right place, we want to infer the following thing. We want to infer the distribution of B and W where, given that S is zero, meaning that we just care about the airplanes that failed to come back. And then we want to change it. We would like those airplanes to come back. What can we do? We have to consider where the holes are, right? For those airplanes. And then we have to put armor there. Right here, 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 and so on. So now if you have this causal picture and observe the data points, you can just answer this question very easily and rigorously. Okay, so summarize, if you want to do active manipulation or intervention to achieve your goal in the system, then we care about the causality. And if you just do passive prediction, giving a particular distribution or giving data points drawing from a particular distribution, then you only care about the association of information or the distribution. And if you want to do a generalization or adaptation, then in most cases, you care about the causality. So tomorrow you are going to see some examples. And if you want to do knowledge integration, most of the time, we really have to make use of causal representations. Here, you can see some examples. Suppose X causes Y, and that Y causes Z, right? Now you see, oh, no matter what, X causes Y and causes Z, right? X causes Y, and then further causes Z. You have a big picture. You have understanding over X, Y, Z together. However, if you know that X, Y are dependent, and that Y, Z are dependent, now what's the relationship between X and Z? You have no idea, right? X and Z can be identical, can be independent, and so on. So if you just make use of association information, you cannot go further. You cannot derive a big picture. But if you really have a causal understanding of the system, you can just have a much better understanding. And that's why we can build aircrafts, right? We know different modules, and then we put different modules together in the right way, then we have the bigger system. And because of causality, we are creative. Let's say we have creativity. So what's the creativity? Essentially, we want to answer the following question. What if something had been different, right? I observe this, and then I want to make a difference. How can I make a difference? I have to imagine something. If something had happened, what would happen, right? This is the difference. And so this is a counterfactual question. And furthermore, you have to answer such question. You have to do knowledge integration and so on. So basically, those things are related to causality. Okay, now let me give a quick introduction to graphical models. Probably we should just stop, pause for 1 minute for questions. If you have questions, please just write. You can raise your hand, or you can just write the questions in the chat window. No? Okay, then let's continue. So right here, you can see a graphical representation of the relationships between a lot of variables. So right here, you have anxiety, peer pressure, smoking, and so on. So with this graphical representation, you can see we have a very nice understanding of the relationships. We know, oh, anxiety influences smoking, and then further influences lung cancer, and so on. This is very intuitive. So this is what we can benefit from graphical representations. Here, a graph has nodes, and we have links to connect the variables or the nodes. And this is the graphical representation. And we use a probabilistic graphical model to encode a complex distribution in a very intuitive and compact way. So right here, each node is a random variable because we are talking about a probabilistic graphical model. We want to model distribution. So each node is a random variable, and each link represents a direct probabilistic interaction between them. Now we are not talking about causality. The link right here, the link is not necessarily causal, but later we have to further attach some constraint to the graphical representation, and then we can make sure that the graphical representations are causal. So essentially now we just combine two things. One is the graph theory, which provides a very intuitive way to see the relationships, and probabilistic theory, which can be used to represent uncertainty in the variables or the relationships. And if you combine them, we have a very nice way to have an intuitive way to represent the distributions. Okay. So we are particularly interested in directed graphical models. And in most cases, we are concerned with a directed acyclic graph in which we don't have any loop. So if you go from one variable, you will not go back. And these kind of graphs are also known as the Bayesian networks or belief nets. Right here, you can see an example. And right here, directed graphical representation graphs or Bayesian networks have two components. One is about the structure, qualitative specification of the relationships. And the other is a quantitative part. We have to attach either conditional distributions or some models to represent the probabilities of some variables given other variables. So finally, we can have the joint distribution of the of all the variables. So for the graphical structure, in many cases, right, we can just build a structure. We can just have the structure based on our understanding of the problem, and sometimes we can learn it from data. And the quantitative part can sometimes be a conditional distribution, and then it can also be some equations, some structure equation models. I will give the definition of a structure equation model later. So in graphical model, we have a lot of terms. Here, right here, they have a node. This is the node. This is the edge. And if there's the edge between them, we say they are adjacent. And right here, we have a path. And in particular, this is a directed path because we just follow the same direction, right? Go from cloudy to sprinkler to red grass. This is a directed path. And this is the path, but it's not directed. And right here, sprinkler and rain are parents of wet grass. They are adjacent, they are causes, they are ancestors. Later we define ancestor. And this is the children. In particular here, sprinkler and rain are the children of cloudy. And sprinkler and rain are spouses because they have a child, which is wet grass. And all the other variables are the ancestors of wet grass. They are either causes, they are either parents or parents and parents or parents, and so on. And all the other variables are descendants of cloudy because they are either children or children's children, and so on. And later we'll have the definition of Markov blanket. Okay. So typically, there are three types of questions related to Bayesian networks. The first one is called probabilistic inference. So right here, we are given this structure, and we are given conditional distributions. And then suppose we know the value of some variable, then we want to infer the probability of some other variable, right? Right here, you want to find the posterior of some variable given the some of the observed value for some other variable. And this is called probabilistic inference. The second one is the parameter learning. So right here, given data, how can I learn, say, parameters in the conditional distribution or parameters in the structured case models and so on. And the last one is known as structured learning. So you want to learn the structure of the graphical model from observed data from a data set. And right here, this structured learning is not necessarily causal learning, not necessarily causal discovery, because this structure is not necessarily causal. For instance, if you have two variables, in many cases, you just want to determine whether two variables are adjacent if you want to learn a Bayesian network. But from the causal perspective, we have to carefully distinguish between different directions, right? Okay, so now suppose you are given this directed graphical representation right here. What independence relationship can you infer or can you see regarding the variables? And right here, to do so, we can apply the so-called local Markov condition. Each variable is independent or conditionally independent from its non-descendants given its parents, meaning that right here, yellow finger will be independent from cancer given smoking, because cancer is the non-descendant of yellow finger. And in this example, falling down will be independent from rain given slippery ground, right? This is the local Markov condition. It's nice because once we have the graphical representation, we can immediately see whether variables are conditionally independent. However, it's probably not enough because in many cases, we want to see whether two arbitrary sets of variables are conditionally independent given some other variables. So in this case, we cannot directly apply local Markov condition. We have to use something different, which is a deseparation. So basically, if you know deseparation relationships, then we have the following thing. If every path from a node in X set of variables to a node in Y, another set of variables, is deseparated by Z, then X and Y are conditionally independent given Z. This is known as the global Markov condition. And here by D, I mean directional. Let you see why, because we care about the direction of the path. Now, definition of deseparation. So we have three sets of variables, X and Y and Z. So we say Z deseparates X and Y if every path from any node in X to any node in Y is blocked given Z. Okay, so every path between X and Y is blocked by Z. Now comes the definition of blocked, right? What do I mean by blocked? So right here, we say a path is blocked by a set of variables Z or set of nodes Z if at least one of the following conditions holds true. If one of them holds true, then we say it's blocked. Of course, if both of them hold true, clearly it's blocked. The first condition says that this path contains a chain I to M to J, or a common cause right here. M is a common cause, such that the middle node M is in Z. So if M is in Z, then you can see right here. If I know M, or if I condition on M, I just cut this off, right? And the second condition said that P contains a collider or common effect, M right here, such that the middle node M is not in Z, the condition set, and no descendant of M is in Z. Now, let's try to understand this condition, or those conditions in light of examples. So right here, we have a directed graph over X, R, S, T, U, V, Y. So do you think X and Y are deseparated by R and V? X and Y are deseparated by R and V? Yes or no? So clearly it's yes, because the first condition, we only have a single path between X and Y, and the first condition holds. V right here is a common cause, it's in Z. Second question, do you think S and U right here, S and U are deseparated by R and V? So S right here, U right here. Do you think S and U are deseparated by R and V? Yes or no? Answer is also yes, because the second condition holds true. We have a collider or common effect here, and we know T is not in the condition set, and no descendant of T is in the condition set. Okay, right here you have you can see more examples. Basically, this is known as a global Markov condition. If X and Y are deseparated by Z, then X and Y are conditionally independent given Z, a condition on Z. Okay, let's give the examples. Okay, so now we have two Markov conditions, local Markov condition and a global Markov condition. If you are dealing with the DEX, then the two conditions are equivalent. So you can prove a global Markov condition by making use of a local Markov condition and vice versa. It's nice because now we can easily see conditional independent relations from graphs. And now comes the definition of Markov blanket. So if you are given a DEG, then the Markov blanket of any node is a set of variables consisting of parents of X, children of X, and the parents of children of X. Basically, other parents of children of X. So, for instance, suppose let's consider I here. Then the Markov blanket of I would be the set of variables E, K, L, H, J, right? Parents, children, other parents of children. And then we have this very nice property. All the remaining variables will be conditionally independent from this variable I, given the Markov blanket. And you can easily prove that. Why? Because all the other variables will be deseparated from this variable I, given the Markov blanket of I. Okay, you can see all paths are blocked by the Markov blanket. Okay, this is the Markov blanket. And we can learn DEX, or we can learn graphical representation from data, right? There are many methods to learn Bayesian networks. So sometimes they are causal, but sometimes they are not. Causality is not just about the conditional independence. In particular, in the two variable case, right? No matter how, no matter which way the direction goes, we say they can represent the same distribution, right? However, from a causal perspective, they are totally different. X causes Y, right? And this case is totally different from the situation where Y causes X. How can we be sure that the DEG representation is causal? Right here, you can see we have a graphical representation. In order to be sure that this is causal, we have to attach some conditions. And clearly, based on the definition of causality, based on intervention, we know we have to introduce the intervention right here. So there are basically three conditions. Here by PXV, I mean the distribution of V resulting from intervention on X. So this is PXV. And then first condition says that this interventional distribution is Markov relative to G. So we still have the conditional independent relations seen from the graphical representation. The second one is also pretty trivial. It says if you do intervention, then the probability for instance here, if you do intervention to set the value of x3 to on, then the probability for x3 to be on is 1. That's for sure, right? You just set the value to some constant, then the probability will be 1. The last one is very important. It says that the interventional distribution, conditional distribution, is the same as the original distribution if I do not intervene on this variable v. So if I do not intervene on this variable, then the conditional distribution of this variable on its parents would be the same across the two graphical representations. Right here, we have, this is the effect of intervention, right? This is the post-intervention distribution. And this is the before intervention distribution. Essentially, the two models will give you the same conditional distribution. In other words, even if you do interventions, you can see I can still use the conditional distribution I have before. In other words, this intervention is local, or we can say this representation is modular. We have separate modules for the causal system. If I do intervention here, then this conditional distribution and this conditional distribution will not be changed by that. This is known as modularity. Okay, this is one way to represent the causal relations. You use the causal directed cyclic graph. So alternatively, we can use the so-called structural equation models or structural causal models. So now we don't use the graph. However, we can use a set of equations. We know x1 causes x3. This is x2. x1 causes x2. Then x2 can be written as a function of x1 and some other omitted factors or noise. And x3 can also be written as a function of x1 and some other omitted factors, e3, and so on. So right here, from this set of equations, you see the causal relations. You know, x1 is the direct cause of x2, x1 direct cause of x3, 2 and 3 are direct causes of 4, and so on. And that's why we say this is a structural equation model, because this provides a mechanism to assign the values to the variables on the left-hand side of the equation by making use of the values of the variables on the right-hand side of the equation. So we use the value of x1 to determine x2, although it's probabilistic, right? We have noise right here. So this is called the structural equation model. And we say each equation represents an autonomous mechanism because we can just change one of them without changing any other variable, also known as modularity. And so basically, we have two ways to represent the causal relations. And then the next part, you'll see how we can learn causality, causal relations from observational data. Okay, now let's try to learn causality as the answer to the previous question. Very good question. So what can we do? Here, for human beings, right, we can learn causality. And in many cases, we make use of temporal information, temporal order information. We know cause is happening before effects. Right here, you can see a problem. Actually, this is a problem in my 4-year-old son's homework. So you can see kids can really determine the order very easily. And also at the same time, you can say, yeah, if this happens before that, then this is the cause of that in some way, right? First of all, yeah, this is reasonable. Second of all, this is not necessarily the case. In many cases, we cannot discover causal information from temporal information. And third of all, in many cases, we do not have temporal information, right? We may have ID data, or we may have very low resolution of the data. Suppose the causality happens very fast, and suppose you have very low resolution of data. What can you do? You cannot just rely on the temporal information. That means we really have to go further to discover, to find the characterizations of causal information in the data, or to find the kind of footprint of causal influence in the data. Actually, we can. And this is very general because once you solve the problem without making use of temporal information, right? Then if you are giving causal temporal information, that's just additional constraint you can make use of. That's why let's just start with a very general problem without temporal information. So here you can see an example. Actually, this is a very nice paper published in Science a couple of years ago. So as you can see from the title, it's a causal problem, say large-scale psychological differences within China can be explained by rice versus wheat agriculture. Means that agriculture causes culture or psychological difference. So clearly, here we don't have temporal information. We don't have the temporal precedence information, right? And we cannot do intervention. You cannot force people to change their agriculture, right? Even if you can do so, you have to wait a very long time to see the effects. That's why in that case, we cannot really do intervention and make use of interventional data. We have to discover causal information by analyzing the observed data. And actually, the conclusion of this paper is rather strong. It says, yeah, they said a history of farming rice makes cultures more interdependent, whereas farming wheat makes cultures more independent. So you can see this is a causal explanation. Also, they try to control for possible confounders like climate and so on. So it's very nice. Right here, mathematically, you can see we have variables x, y, z. They can be a set of confounders, and they just discover a set of independence and dependence relationships, conditional dependent relationships. And then under some very mild assumptions, they can say x causes y. That's very nice. That's how you can discover causal information by analyzing data. You will see the procedure. This is another example. Right here is my collaborator, Marlene Nobeck. Her last name is very cool, Nobeck. Just go forward, look forward. So she collected she collected 250 skeletons all over the world. And she measured 8 variables, including gender or sex, cranial size, diet, and cranial shape differentiation. So essentially how it looks. Essentially, in archaeology, they really want to see how and why people from different areas look different. And also based on the understanding, they want to make prediction into the future. So that's very nice. Clearly, you cannot do intervention. You cannot wait to see the effects of interventions, right? You have to analyze those collected data skeletons. Later, you see the results. So, okay, now let me give some basic concepts. The first one is the causal sufficiency. Here we have a set of variables, V. We say V is causally sufficient if V contains every direct cause of 2 variables in the system in V. Right here, you can see we have Z, X, Y, and Z is a common cause, direct common cause of X and Y. And if V is Z, X, Y together, we say it's causally sufficient. And if V is just X and Y without Z, we say it's not causally sufficient or causally insufficient. Why? This is because the direct common cause of X and Y, 2 variables, which is Z, right, is not in the system in V, the set of variables. That's why we say this set of variables is causally insufficient. Most methods for causal discovery assume causal sufficiency. So basically that means there are no missing or there are no unmeasured direct common cause of 2 variables in the system. And also we define confounder this way. Confounder is the unmeasured direct cause of 2 variables in the system. So if right here V is just X and Y, we say Z is a confounder. However, some methods can handle confounders. For instance, the FCI, fast causal inference method, can still give the right results, even if there are confounders in the system. And later you'll see some examples. Okay, this is the causal sufficiency. And the second thing I want to emphasize is called V structure. Right here, you can see we have 3 variables: cold winter, snow, slippery ground. We have this particular structure, right? The 2 causes are going to this variable. This is called a V structure. And sometimes this is also called unshielded collider, because we have this common effect and they are not shielded. So this is particularly interesting. Why? This is because among the 4 causal structures with the same adjacency, you can see right here, this one is totally different from the rest, the remaining 3. Right here, we can see, oh, this is the first case, this is second, third, and fourth, right? In the first case, according to Markov condition, local global Markov condition, we know cold winter is independent from snow, and they are conditionally dependent given slippery ground. Right here, you can see that because this separation, right? Or we can say they are independent, originally independent, right? Given this variable, we don't know, but we know that they are not conditionally independent according to the causal markup condition. However, in the remaining cases, all those three cases, we see the same set of independence relations. We see, oh, cold winter will be conditionally independent from snow given slippery ground, right? So in all those three cases, we see the same set of conditionally independent relations. Okay, let me just have a look at the chat window because I saw something, saw some message. Oh, not a question, thank you. Okay, so here, now you can see, oh, if I know the skeleton, right here, by skeleton, I mean the adjacencies without directions, then I can distinguish between this particular case and the remaining cases by making use of conditional independence between the variables. Okay, this is very important. Now, let's try to do causal discovery. The definition of causal discovery is as follows. We are given observational data, and you want to recover the causal structure or some essential information of the causal structure by analyzing the observational or non-experimental data. So now what can we do? We want to go from data to the graph, right? So how can we connect the two things at different levels, right? First of all, we have markup condition. For instance, if you apply global markup condition, we have the following thing. If two variables are deseparated by another variable z in the graph, then we know they are conditionally independent, right? So we can go from graph to independent relationship, independent relations. How can we go back? First of all, if you want to go back, you have to apply something like counterpositive of this proposition. That means if you see conditional dependence between x and y given z, then x and y are not deseparated or deconnected by z, right? So this is the counterpositive of the proposition. What if the variables are conditionally independent? You have no idea, right? We only know that, oh, if they are conditionally dependent, then they are deconnected. If they are independent, we have no idea, according to this global markup condition. And if this is the case, for any data, we can always give a graph to satisfy the markup condition. What graph? We can always use a fully connected graph, right? Each pair of the variables is adjacent. Then you can see global markup condition, this guy is always true. Because this guy says, oh, if they are deseparated by z, they are conditionally independent given z. In this graph, fully connected graph, no pair of variables is deseparated by any other variable. As a consequence, you can say, oh, I cannot see conditional independent relations in the data. If you really see that, it could be something you observe by accident, right? It's not necessarily the consequence of this condition, meaning that this condition still holds true, right? Because if the condition is violated, then we cannot say anything about the conclusion. So this solution is trivial because you always provide a fully connected graph. How can we find a simple informative graph from data? That means we have to make use of conditional independent relations in the data. In other words, how can we go from conditional independent to deseparation, right? Go from the right-hand side to the left-hand side. Now we need two things. One is the markup condition, you know that. If you know the graph, then each variable is a conditional independent from its non-descendant, or we can say if two variables are deseparated by the third one, then they are conditionally independent in the third one. This is a markup condition. In addition, we have another condition called faithfulness. So faithfulness says that all observed independence or conditional independent relations in the variables are actually entailed by markup condition on the causal graph. It means that if I observe the independence between y and z given x, then this is the property of the graph. If you apply markup condition and observe this conditional independence, you know that, oh, y and z must be deseparated by x. In other words, now we can go from conditional independent relationship to deseparation. Okay. So this is the faithfulness condition. And the faithfulness condition is very interesting. You can just think of faithfulness condition as something like a faithfulness relationship between a couple, right? That there's some kind of one-to-one mapping between different things. Okay. So again, faithfulness assumption says that all observed independent relationships are actually properties of the graph according to the Markov condition. In other words, there's no accidental independence relationship in the data compared to the graph or compared to the set of relationships implied by the Markov condition on the graph. Okay, think about it. Make sure everything is natural to you. Now, let me just say a few words about the faithfulness assumption. In this example, with the 3 variables, health condition, healthy lifestyle, and then mortality risk. Let me have a look at the chat window. Okay, let's just pause here. We have a question from Shreya. What is the intuition behind the concept of deseparation and behind the deseparation conditions? Okay, so deseparation is just a property of the graph, right? So essentially, by deseparation, intuition is as follows: if x and y deseparated by z, then they are given. If you know z, if you condition on z, then there is no other way for x and y. No way for x and y to be related in the graph. This is intuition. Let me just go back. So here, this is the picture to give some kind of intuition. We have variables A, B, C, D, E, F, G, right? And here we can just use the basically here we can just use the tabs. And giving something means that this guy is turned off. So if giving C, then this one is turned off. Okay, now you can see deceleration. We can see clearly A and C will be deseparated by B. Why? Because if you turn off B, the connection between A and C will disappear. In other words, they are separated by B. This is deseparation. And also you can see, A and C will be conditionally independent because there are no information flow from A to C or from C to A. And they do not share any common information, right? And similarly, you can see, probably that's enough. So deseparation is a property of the graph. And if A and C are separated by B, basically, that means if you hold B, or if you condition on B, there is no way for A and C to be connected, to be related, according to the mechanisms. Is that the answer to your question? In case it's not clear, please just give me some hints. Okay, faithfulness. Now, in this example, we have 3 variables, and not surprisingly, we have this causal graph. Health condition influences affects mortality risk, and okay, questions. Health. So deseparation is a separation between 2 connected components. If I understand correctly, yes. So deseparation is the relationship between involving 3 things. So it's the relationship between 2 variables giving another variable, or the relationship between 2 variable sets giving another variable sets. Okay. So here, this is the causal graph. We have, suppose it's linear with linear coefficients. Causal strength is A, B, C, right here. If by accident A equals minus BC, what will happen? Now you can see health condition will be independent from mortality risk. although the former is actually a cause of the latter, right? And you cannot see this independent relationship from the graph by applying Markov condition, right? They are not disseparated. Actually, they are not disseparated by anything. Why? Because we have an edge between them. If there's edge between them, you can never disseparate them by giving anything. So this is the violation of faithfulness. And in this case, you can imagine why faithfulness is violated. You can imagine why those two variables, although causally connected, are actually independent. This is because we have other things. We also have selection process, right? We want to optimize a lot of things in this process. This is the only part of the causal graph. We want to enjoy a life, right? We want to enjoy our life. That's why finally health condition can be independent from mortality risk. So here, by assuming faithfulness, we just get rid of this possibility, meaning that if we have this causal graph right here, then health condition cannot be independent from mortality risk. Okay, and generally speaking, that's true. Why? Remember modularity. So the process, the generating process for this variable specified by a particular structure equation model is not related to any other structure equation model. In other words, A and C here shouldn't be related to B at all. They are chosen independently by nature, right? And if that's the case, then the condition for this equality to hold true would have measure 0. That means, oh, if this is really causal graph, then the violation of faithfulness has measure 0. In other words, in most cases, we should trust faithfulness assumption. Of course, if you have finite data, it's possible that the faithfulness assumption is approximately violated, right? That's another issue. And there are some very nice papers trying to deal with faithfulness. So you can just search, you can just do a Google search if you want to see how to deal with the violation of faithfulness and how to detect the violation of faithfulness and so on. For now, we assume faithfulness. Okay. Now, given this, we can do causal discovery. And we are going to see two types of classical methods for causal discovery. The first one is called constraint-based method, condition independent-based method, and the second one is called score-based method. We start with the constraint-based method. Now, we have two questions to answer. We have data. From data, we discover independence and conditional independent relations, right? First, how can we find the skeleton of the causal graph? Is it possible? If yes, how? The answer is yes. Later, you will see why. And second, can we go further? Can we determine the causal directions? Yes, we can determine some of the causal relations. Here, you can see, basically, you can see how we can solve the problem. So we want to make use of independent and conditional independent constraints to find the essential information of the causal structure. We now assume causal Markov condition, which is kind of widely assumed, and the faithfulness assumption, a typical assumption for causal discovery. And the typical method is called the PC algorithm. P is for Peter, C stands for Clark. So it's Peter Spertis and Clark Glimmer, basically the first letters of their first names. They are my senior colleagues that came up with a lot of classical methods for causal discovery. Now, as the answer to the first question, remember, we want to find the skeleton or adjacency information of the graph. Then we have this theorem. It says that if two variables x and y are adjacent, two variables x and y are adjacent if and only if they are dependent, conditioning on every subset of the remaining variables. In other words, as long as x and y are conditionally independent given anything, then they are not adjacent, right? This is very nice. And you can prove this very easily. Why? Because if they are conditionally independent, then they are disseparated by something. If they are disseparated by something, then they are not adjacent, because any two variables that are adjacent cannot be disseparated by anything. Okay, this is the first part. We, by doing conditional independence tests, we can find the adjacency information. And then we want to find the directions. Remember the definition of bit structure, right? Right here, you can see, if we have this ground truth, then we have the independence between y and z given x. And then we cannot determine the causal structure. All those three possibilities will have the same conditional independent relationships, right? However, in this case, if we know we have three variables x, y, z, if we know that y is independent from z, then we know all y and z must be causes of x. This is bit structure. So if you discover this structure, you can determine the causal direction. And then you can go further. You can do orientation propagation. Later you can see how we can do so. And in general situations, we may not be able to find a unique structure, and we have to represent the set of solutions by a pattern. And this set is known as the Markov equivalence class, because all members of this class will have the same conditional independence or independence relationships over the variables. Later you will see the definition. So let's have a very quick look at the procedure. So here we have data, x1 for x1, 2, 3, and 4. From data, we can discover independent conditional independent relationships in some way. So suppose we have an oracle procedure to infer independence and conditional independent relations between the variables from data. Now, since 1 and 3 are independent, we know they cannot be adjacent. Since 1 and 4 are independent given 2, we know they are not adjacent. The same thing happened to 3 and 4. And then we can go further. Right here, 1, 2, and 3 form a bit structure because 1 and 3 are independent. We know causal structure, causal direction must go this way. And then we know the direction between 2 and 4 must go this way. Otherwise, if it goes this way, we are going to have a bit structure, which is fake. We can determine whether it's a bit structure. If this is a bit structure, then x1 and x4 would be independent, but they are not. That's why it's not a bit structure. If it's not a bit structure, then this direction must go this way. Okay, so this is what we can do. Now you can see another example. I'll give this example step by step. So suppose we have data generated by this causal graph you just saw, and then we begin with this fully connected graph or complete graph in which each pair of the variables is adjacent. There's edge between them. Then first we start with the unconditional independence tests. Now we can see, we just consider each pair of the variables. We see 1 and 2 are independent. Then we can get rid of this edge. For all the remaining pairs, they are not independent, conditioning on nothing. So this step will stop, and then we go to next one, where we condition on a single variable to see whether variables are independent. And then we see when 1 and 4 are independent, given 3, we get rid of this edge. And furthermore, we see 2 and 4 are conditionally independent given 3, and we can get rid of this edge. And then, according to the PC procedure, we will stop, because for PC, every time we just need to condition on a subset of the adjacent variables. Now it's enough. We don't have to condition on 2 variables. So we'll stop here. This is the first step. We just found the skeleton of the causal graph, and then we find the bit structure and then do orientation propagation. Right here, 1 and 2 are independent. Then we have this bit structure, as you can see from this bit structure, and then we do propagation. So propagation has 4 rules, and they are complete, meaning that if you can orient this edge, then by making use of one of the 4 rules, you can do so. So here you can see 2 examples. The first one is to avoid fake or spurious bit structures. I know this direction. I don't know this direction right now, but I know this is not a bit structure. Why? Because all bit structures were already discovered at the beginning of step 2. Then I have to orient this guy this way, because otherwise I'm going to have a fake bit structure. And this is a away from cycles. Right here, I know this direction, and then for this one, I have to go this way, because otherwise I'm going to have a cycle violating the assumption of DAG, directed acyclic graph. Later, you can see how we can deal with cyclic graphs with loops. But right now, we assume the graph is acyclic. Okay, now you can see the solution. Now, how you can see in this example, we have directions for all edges. But in many cases, we don't have direction for all edges. We have to represent the solutions. So first of all, we say two DAGs, directed acyclic graphs, are independence equivalent or Markov equivalent if and only if they have the same skeleton and the same V structures. Okay, and then we can use the patterns or CP-DAG, completed partially directed graphs, to directed acyclic graphs to represent the equivalence classes, a set of equivalent DAGs. So essentially here you can see how we can do so. In total, there are only 3 possibilities for the edges. Right here, they are not adjacent. Right here, they are adjacent, but we don't know the direction. It means that, oh, in some members, the direction goes this way, and in some other members, the direction goes this way. We cannot determine it in the solution. That's why we don't have the direction. And right here, it says that, oh, I know the direction. Direction must go from 1 to 2. Then we can just use the directed edge. So, okay. And this is a pattern to represent the Markov equivalence class. So in this Markov equivalence class represented by this pattern, in total, how many DAGs do we have? How many possible solutions, how many possible DAGs are contained by this pattern? Maybe you can give an answer right now in the chat window. So I wait 5 seconds. How many members, how many DAGs can be represented by this pattern? Okay, no one. So in total, clearly, right here is 2, right? It's just 2. It can go this way or that way. Okay. Now come the second example. Suppose we have data, enough data, right? With a rather large sample size. So generated by this graph, then we can do the same thing. We start with this complete graph. Right here is just the edge between A and E. It's ugly, but it's just a direct, just an edge. So we start with the unconditional independence test. Right here, no pair of the variables is independent, conditioning on nothing. And then we condition on 1 variable, and then 2 variables, and so on. So finally, we can stop here, and this is the skeleton. It's correct. And then we can find a V structure right here. CDE form a V structure. Why? This is because C and D are conditionally independent given B, which does not contain this variable. That's why we know, oh, right here, C and D must point to E. Otherwise, if one of them goes in a different direction, then in order to make C and D conditionally independent, E has to be part of the conditioning set, right? In order to make them de-separated, we have to condition on this guy. Otherwise, this path is always open. If you do not condition on E, suppose the direction goes this way. But if the direction goes this way, we cannot condition on E. If you condition on E, they will become conditionally dependent. Okay, so now we have this graph, this pattern. Do you think we can determine the direction between A and B, or between B and C, or between B and D? Yes or no? In this case, no, we cannot go further. We cannot determine directions. And then a quick question. This is the pattern. How many graphs, directed acyclic graphs, can be represented by this pattern? We know right here direction can go this way or this way. And right here can go this way or that way, and so on. So in total, how many graphs, directed cyclic graphs, can be represented by this pattern? Good, good. So I'm not going to give you a solution, but I want to give a wrong answer. Some people may say 8. Why? Because here I have 2 possibilities, here I have 2 possibilities, and so on. So the total number of possibilities would be 2 times 2 times 2, which is 8. It's wrong. Why? Because we cannot have a fake V structure. We cannot allow 2 of them, this one and that one, to go to B at the same time, because if that's the case, we are going to have V structures, right? So we can just consider all possibilities that will not introduce any fake V structure right here. Then you can do a calculation. You can immediately find the solution regarding the number of possible decks in this pattern. Now let's have a quick look at some real applications of this search procedure. Sometimes we say causal search because you want to search for the causal structure. Right here we have data for sex, IQ, CP, college plans, PE, parental encouragement, SES, socioeconomic status of the family. And the data were collected basically from more than 10,000 high school seniors. And this is the graph given by the domain experts right here. Actually, they apply the method, my colleagues apply the method, and they recovered almost everything in this ground truth provided by domain experts. Almost everything with a single difference. From this graph, can you guess what the difference is? For instance, can we recover the direction between SES and IQ? No, this is the only difference. Right here, with the solution given by PC, will give an undirected edge between SES and IQ because we cannot determine the direction right here. All the remaining edges are directed because we can determine the directions. For instance, here, for this one and that one, this is a V structure. SES, sex, and PE, the V structure, and so on. So now you can see we can really recover information about the causal relations by analyzing observational data. And in this case, if you use PC, sometimes we cannot recover the complete information, but we can trust the information if you have enough data. This is the second example, which you just saw at the beginning. So you can apply PC combined with our kernel-based conditional independent test, because here we cannot really assume the relationships are linear. They can be very complex. So we use the non-empirical method for conditional independent test. Right here, you can see the result by PC combined with this test method. Some of them, some edges are directed, some are not. So right here, you can see if you have some background information, for instance, we know location. This is location, this is climate. The direction should go from location to climate, not the other way around. If you introduce such information, then you can do orientation propagation. This guy must go this way, otherwise I have a fake V structure. Hey, immediately we have a deck. Now we have a complete deck, directed cyclic graph. A lot of the information right here has been discussed in the literature. For instance, here, climate and cranial size. So basically, if it's very cold, like in Russia, right? People tend to have a larger cranial size because it's better to warm the air before you really inhale the air, right? So the cranial size would be larger. From the selection perspective, you can explain why we have this causal inference. However, we can still discover something novel compared to the information that discussed in the literature. Right here, in the literature, they say the diet is a cause of cranial shape differentiation, which means what you eat will change how you look. It's fine, right? However, here, yes, we agree, but at the same time, we can see that relative to this set of variables, diet is not a direct cause of cranial shape differentiation. When we have an age, we just mean that, oh, this guy is the direct cause of that guy. So right here, by analyzing data, we have not only causal information, but also very detailed information regarding whether this variable is a direct or indirect cause of some other variable. And this is detailed because we know that diet influences cranial shape differentiation via another two variables, including level of attrition in teeth and some behavior. So now data analysis is really cool because I can really discover very detailed information regarding the variables. If you just make use of domain knowledge, it's really hard. Okay, good. Now let's have a look at some particular examples. So far, we have assumed that there are no confounder in the system. In other words, we assume causal sufficiency. There are no unmeasured direct cause of two variables in the system. Okay, now let's look at the examples. We want to answer the following question. Is it possible to say anything about the confounders? Example 1. We see independence between 1 and 2, independence between 1 and 4 given 3, and independence between 2 and 4 given 3. Okay, this is the graph. Previously, we already have this. Now, the question is, do you think it's possible to have confounders behind 3 and 4? Yes or no? Is it possible to have this confounder, C? The answer is no. Why? Because if you have this confounder, then x1 and x4 will not be separated by 3 because of this path. If you condition I3, this path will be open. In other words, x1 and x4 will not be independent given x3 if you have this confounder. But now we know 1 and 4 are independent given 3. Then we know there are no confounder. And furthermore, we know in this case, no matter what, right? We know x3 is a direct cause of x4 without the confounder. This is super cool because by analyzing only very few variables, we can really say whether it's possible to have a confounder. We can say something very universal, right? That's cool. We can exclude the possibility of having confounders. Okay, this is the first example. Second example. You can just have this is example. So let x1 be rainy, and this is wet ground, slippery. Now you can see, oh, as long as I know that x3 is not the cause of x1, and then given the independence between x1 and x4 given 3, I know that x3 must be a direct cause of x4 without the confounder. Okay, example 2. 1, 3 independent, 1, 4 independent, 2 and 3 are independent. From this, you can immediately write down something, right? You know, oh, 1, 4, 1 and 2 are adjacent, 1, 4 not adjacent, 1, 3 not adjacent, 3 and 1 not adjacent, 3 and 2 are not adjacent. So basically, we have this. For now, just ignore arrow, right? And now, do you think they're the confounder between x2 and x4? The answer is yes. There must be confounders behind x2 and x4. First of all, if there are no confounder, then you can see 2 and 4 must be adjacent. And if the direction goes this way, from 2 to 4, to save time now, yeah, let's spend some time here. If this guy goes this way, now you can see, oh, x1 and x4 will not be independent because we have a directed path from x1 to x4, right? So this guy cannot go this way. And similarly, this guy cannot go this way. And how can we explain the phenomenon? We have to introduce a confounder. Actually, there's a confounder behind the x2 and x4. This is the only possibility. Okay. So here, in this case, we know although x2 and x4 are dependent, and they are conditionally dependent given anything, still we can infer that there must be confounders behind x2 and x4, and furthermore, that there's no direct causal relationship between x1 between x2 and x4. They are not directly causally related. They are dependent because of the confounder. Okay, you can think of examples. So let x1 be whether I'm sick, 2 whether I'm in this lecture room. Suppose we are in the room. X4 is whether you are in the room, and X3 is whether you are sick. Whether you are sick. So now you can see, you can verify those conditions. 1 and 3 are independent, 1 and 4 are independent, 2 and 3 are independent. Of course, we can make this more general. We can just condition on a lot of variables, doesn't matter. Now, given this, I can just infer that X2 and X4, although dependent, are not causally related. They are confounded. So I'm in this lecture room, you are in this lecture room, right? Because of something hidden, because we have a lecture here. So even in our daily life and in history, in social sciences, we can make use of such rules to discover causal information by making use of the observed information. Okay, so just now you just saw something about whether we can determine confounders. More generally, the problem that follows.
We have about 2 minutes left, so maybe we can do a small recap before starting a new topic.
Yeah. Since we started a little bit late, so could you give me 3 minutes?
Of course. Yeah. All right.
Okay. So then, because I have to finish this part, otherwise, yeah, probably we have to go from the beginning next time.
Yes.
So yeah, to make it to formalize the problem, now we have this issue to address. We have a direct cyclic graph over a lot of variables, right? Like you can see from here, we have a direct cyclic graph over x1, 2, 3, 4, and L. But unfortunately, we only observe some of them, x1, 2, 3, 4. This guy is not observable. Then we want to analyze the information between the observed variables, right? So in this case, as you can see from this example, the observed variables may not follow a DAG or directed cyclic graph. If you use a DAG, you have no idea, you have no way to represent the dependence or relationship between x2 and x4, right? So here, what can we do? We have to use another thing called a PAG, partial ancestral graph, to represent the relationships between the observed variables, to represent the relationships between the observed variables, given that the causal relationships happen to a larger set of variables, including this observed set of variables, right? We have additional variables omitted in the system. So here, all those methods or those examples have been considered in the FCI method. FCI is the fast causal inference, published in the 1990s. So right here, we cannot use a pattern to represent the output of FCI. We have to use, in other words, we cannot use CPDAG, completed partial and directed cyclic graph. We have to use PAG. So for PAG, in total, we have 5 situations. We have 5 possible edges. Not adjacent. X2 is not an ancestor of X1. No set deseparates X1, X2. Right here, X1 is the cause of X2, and there must be a confounder. So in total, we have those 5 possible situations regarding the edges. Okay, so I'm going to stop here, and let me just give a very quick summary. Next time we'll start from here. So yeah, okay. So first of all, the key message is that the conditional independent relations can be used to discover information of the causal structure. And to do so, we have to make assumptions. One is the causal markup condition, the other is called faithfulness. You know what's there, and you know in what situations faithfulness assumption is violated, and you know why in a general situation this condition should hold true. And then we can develop the constraint-based method. Here by constraint, I mean conditional independent constraint. And we can also discuss, we can also consider or deal with confounders under some assumptions, as you can see from the FCI method. last time I talked about why we care about causality, what we can benefit from causal modeling or causal thinking, and I talked about how to make use of conditional independent relations to discover causal information. Give me 1 second, I need to turn on light. Okay, so basically this is the outline, and this is what I talked about in part 2 in the second session. Including the PC algorithm, FCI, the basic idea of FCI algorithm. And I'm going to talk about GS method, which is the typical score-based search method, causal search method. And then we'll have a very quick look at some extensions of the constraint-based method for causal discovery to deal with the practical issues in complex situations. Okay. Now, last time I asked you, do you know how many decks we have right here in this case? How many decks can be represented by this pattern? Remember? Yes, the answer is 4. After the talk, I saw and some of you gave the answer 4. Great, it's 4. Note that the directions of different edges are coupled, right? Because we cannot have fake these structures. Very good. And then this is particularly important because a lot of people say, yeah, you cannot do causal discovery because there can always be confounders, unmeasured derived common causes. But here with those examples, you can see, yes, right here, we are sure that there are no confounder behind the variables. And we are sure that X3 is a derived cause of X4. And sometimes this is known as Y structure because you can see it's Y. And in this case, we know there must be confounders. And we know that there are no direct causal relationship between the two variables, X2 and X4. Good. And then right here, you can see an example of application of the Y structure. You may see the detail later. Let me just give the key information right here. By making use of conditional independent methods, they discovered the Y structure and concluded that the pH value of water or acidity of water is the only direct cause of the biomass of the plants near the electric company. So that's very strong conclusion. And later, this claim was verified by intervention-based analysis. So causal discovery methods are really useful. You can discover very strong information by making use of conditional independence relations. And then, basically, PC algorithm contains those ideas regarding how to detect confounders and how to find the causal relations in the presence of confounders. And as a consequence, we cannot use patterns right here. You cannot use a pattern to represent the output of PC, of FCI. Why? This is because if the original set of variables follow a DAG, then the observed variables as a subset of the whole, variable set cannot be represented by, usually cannot follow a DAG. That's why we have to find something more general to represent the relationships between the observed variables if you allow confounders. And right here you can see it's different from pattern in which we have 3 possible edges. Now we have 5. And you don't need to really see the detail of FCI, which is very complex, but it's nice to have a very nice interpretation of the result of the output of FCI. So right here, you can see, you see this pattern before, you see this edge before, this edge before. Right here, X1 and 2 are not adjacent. Here, X1 is the cause of X2. And here, if you see this, this means there's a latent confounder, or there are latent confounders for X1 and X2, and that there are no direct causal relationship between X1 and X2. And right here, we have circle. What does it mean? Circle just means that right here, we can have either an arrowhead or arrow tail. So either head or tail. If it's a head here, then we can say, oh, they are confounders for X1 and X2. If this is arrow tail, then we can say X1 is the cause of X2. This is how to interpret the output of the FCI algorithm. Okay, now remember this example. This is the second example. Right here, we have 4 variables, right? And now we have a compounder. We generate the data from this graph. Suppose we have enough data. So what do you think would be the output of FCI on the observed variables x1, 2, and 3, and 4? So actually it's this. We are sure that there are confounders between C2 or X2. I use different, sorry, I should use X. So we know there must be confounders between or behind X2 and X4. Right here, we don't know. What does it mean? This means, oh, C1 may be the cause of C2, or there could be confounders for C1, C2, or a combination of them, right? We don't know. From this example, you can see that the FCI result is, first of all, asymptotically correct. Second of all, it might not be very informative. Why? Because whenever it's possible to have a confounder, the result will tell you that, yeah, so you can see it's possible to have a confounder. In other words, we don't have very many directed edges, just directed to show that one variable is the direct cause of the other. Okay, in some cases, for example, if you have Y structure, then you are sure that X3 is a direct cause of X4, but that does not happen very often. That's why we say the result of FCI is correct, but it's not very strong. Later, you can see we can make use of other methods to make the result, called discovery results, much stronger. Okay, so now you see how PC works and the basic idea of FCI. And now let's have a very quick look at another set of methods known as score-based search methods. And this is the procedure. You have data right here, and you have a set of candidate causal structures. And then you want to see which of them gives the best score according to the data. And then you just want to find the best one. So this is score-based method. So in particular, GES, greedy equivalence search, is very popular. This method achieved a lot of attention, a lot of applications, and a lot of attention in the community. So here the assumption that follows. First of all, we assume the score that is used for search, for causal search, is equivalent, meaning that it assigns the same score, same value to equivalent DEX, to Markov equivalent DEX. Second of all, the score is locally consistent. So if you add an edge that can eliminate some false independence constraint, then the score would be better. And finally, the score is decomposable. The total score is the sum of the individual scores right here. Each term corresponds to a particular random variable as the effect. For instance, BIC score satisfies those conditions, and BIC score has been used in GS. So this is very tedious, but basically, just like many greedy search procedures, GS has 2 steps. The first step is forward search. The second one is backward deletion. So in the forward step, we just keep adding edges until we cannot further improve the score. And then we go backwards. We just want to delete those unnecessary edges. Here you can see examples. Right here, suppose this is the ground truth. Then the GS result may be like this. So suppose the correlation between X and Y is strong. First we have this edge, and then we add the second edge. Here we just consider all possible equivalence classes. That's why in the first one, we don't have direction, because this is the representation of the equivalence class. And the second one, we must have the directions. Why? This is because we have base structure. And then we will stop because we cannot add any additional edges to further improve the score. And we do the backward deletion procedure. And in this case, we cannot get rid of any edge. So we will stop. Second example, right here you can see X causes Y via a lot of other variables. So in this case, let's suppose all those causal parameters are similar and are positive. And then you can imagine that the correlation between X and Y could be very high because of the multiple pathways right here. And then it's not surprising that first, GS will add the edge between X and Y because the correlation between X and Y is very high, right? If you add this edge, you can improve the score most. And then you can keep adding edges. And finally, you can see that after the first step, you are going to have an extra edge, which is between X and Y, right? That's why we have to use the second step, which is the backward deletion process. So now we can see, oh, given the remaining edges, the edge between X and Y is not useful. We can just get rid of this guy. As a consequence, after that, we can get the correct equivalent class of the causal deck, original causal deck. So this is the GS method. And then let's have a quick look at some extensions. First, in many cases, in many applications, especially in healthcare, we have missing values, right? In a data set, we have a lot of missing values. And you have to extend the method to handle missing values. And first of all, we observe that the conditional independent relations in the data are very sensitive to the missingness mechanisms. What does it mean? It means that if you just consider the pairs of variables or set of variables and just make use of the complete record in which you don't have missing values, then the conditional independent relations right here could be very different from the conditional independent relations implied by the original true deck. Okay, this is because of missingness causal mechanism. Right here, you can see some missingness graph. So this is one way to represent not only the causal mechanisms between the given variables, but also why and how the data are missing. For instance, here in the first graph, Ry is the indicator of whether the value of y is missing. If the value of y is missing, then Ry has value 1. If not missing, then the value is 0. Okay, so this is the variable now. In this case, Ry, the random variable, missingness random variable or missingness indicator, is independent from all those observed variables. In this case, we say it's missing completely at random, MCR. And in this case, you can see the missingness indicator of y depends on W. W does not have missing values. Then this is the case of missing at random. And in the third situation, Ry depends on W, and furthermore, W also has missing values. In this case, we say it's missing not at random. In all those situations, we can do something to recover the conditional independent relations in the whole population by analyzing the records with missing values. And this is why we can still do successful causal discovery even if we have missing values. So if you are interested, you may have a look at this paper. Okay. And the second problem is about non-stationarity or heterogeneity of the data. So in practice, very oftentimes we have either non-stationary data where the distribution of the data can change over time, or heterogeneous multiple data sets where the distribution of the data can change across different data sets because of different collection conditions or experimental conditions. For instance, if you have observational data and interventional data, clearly distributions are very different, right? Because of interventions. So right here, we have to leverage all data sets or all data together to find the causal information. And in this case, we can benefit from one very important property of the causal systems, which is about the relationship between causal modeling and distribution shift. So basically, causal modeling and distribution shift are heavily coupled. What does it mean? So if you know that X causes Y without a confounder, then we know that the process to generate X, the cause, is completely irrelevant to the process to generate Y from X. So this is known as, again, modularity. We have irrelevant or independent modules to generate the data, right? In other words, if you have non-stationarity or if you have distribution shift, then the distribution of cause and the distribution of effect given causes would change independently. Otherwise, you have to explain the dependence between them. You have to introduce common causes, right? So yeah, probability distribution of cause and the distribution, conditional distribution of effect given cause would change independently. And right here, you can see, yeah, if you know it's causal, you can say something about how the joint distribution can change. And On the other hand, if you see the distribution shift phenomenon, then you can verify that, and you can find the causal information without much difficulty. That's what we are going to make use of to discover causal information from non-stationary or heterogeneous data. Here we assume that the causal structure can change over time across datasets, right? You can see, oh, causal strength can change, and sometimes we have extra or missing edges somewhere. Doesn't matter. So in this case, we can find the whole causal graph, and also we can find where the causal models can change. So right here, suppose we have 4 variables, V1, V2, V3, and V4, right here. And suppose we have a confounder, G, C. Right here in this framework, we assume the confounder can be written as a function of the surrogate variable. The surrogate variable is either time index for non-stationary data or the domain index if you have multiple domains or multiple datasets right here. So now we just have observed the data for V1, 2, 3, and 4. What can we do? Or what should we do? First, we want to determine for which variables the causal mechanisms change. We can do so. Now, first step, we say, oh, V1, V2, and V4 have changing mechanisms. And second, we want to find the true causal skeleton. With our method, yes, we can, even if there can be confounders. And third of all, we want to find the causal directions. And here we benefit from the property that probability distribution of a cause and probability distribution of effect given cause change independently, right here. And finally, if you know that the causal mechanism for certain variable changes over time across domains, you want to find a low-dimensional representation of the changes, right? To see, oh, why and how the mechanism change. So we developed a non-empirical method known as the kernel non-stationary driving force estimation to find such representation. Okay, so now to make it very short, first we apply some constraint-based method like PC to the variable set, to the set of observed variables, and also the surrogate variable C, the index variable. And then any variable that is adjacent to C will have changing mechanisms. Okay, so this is very cool because it's very simple. We can immediately determine for which variable the causal mechanisms change. And then we want to find a direction with the independent changing principle. So basically we know what it means. And then this is a generalization of invariance, because if one of them does not change, then clearly they are independent because a constant is independent from anything. And this independent changing principle is generally violated for wrong causal models. And then here you can have a look at some special cases. In this case, we have 2 variables, Vk and Vl. One of them, which is Vk, is adjacent to C, meaning that the causal mechanism for Vk changes. Okay, and then we can immediately determine the direction between Vk and Vl. So if C, the index, and Vl are independent, given a subset of variables which do not contain Vk, then we know, oh, this is a V structure. Both of them point to Vk. In other words, the distribution of Vl will not change. We say this is the invariant cause. And furthermore, if C, the index, and Vl are independent given a variable set containing Vl, then we can say, oh, this is the chain structure. Because we know C causes Vk, then we know the direction between Vk and Vl. Vk is the cause of Vl. So in this case, you can see although the distribution of Vk and the distribution of Vl changes across domains or over time, the causal mechanism from Vk to Vl will not change. So we say this is an invariant mechanism. Essentially, invariance is just a special case of independent changes. And if both of them, both variables are adjacent to C, then we just need to verify whether they change independently, whether this condition holds true. And because this property, we can find the directions. Okay, right here you can see application. we analyze the daily returns of more than 80 variables in NYSE, New York Stock Exchange. And right here you can see we can find the directed graph. And furthermore, we can just visualize the non-stationary driving force of the change in the mechanisms for different variables. And this is for a USB company. It's interesting because we can verify that this driving force is clearly associated with the risk in the market. Right here, this is 2008 financial crisis, and this is 2007. You can see actually in 2007, the risk is already very high, but in 2008, the risk is extremely high. That's why we had the financial crisis. Okay, so from data daily returns, we can really analyze their causal relations, and we can explain why the mechanisms change over time. So right here in this part, we can see that conditional independent relations can be used to discover causal information. We see what assumptions are needed. Essentially, we need a causal markup condition and faithfulness assumption. And then constraint or conditional independence constraint-based methods were proposed, developed by pioneers in the community, because those methods were developed at the very beginning of the 1990s. Some methods can handle confounders. However, later you can see we can, under some further assumptions, we can handle confounders in a better way. And in practice, if you do causal discovery, you have to analyze the given data, observe the data. The observed data were generated by not only the underlying causal process of interest, but also the sampling process, measurement error, and so on. That's why we have a lot of practical issues to deal with. So right here, you just saw that how we can deal with missing data and how we can deal with non-stationarity or heterogeneity in the data. Okay, now let's have a look at part 3. We are going to see those methods and ideas that were developed in the last 15 years, more recent. So in this part, first I will present linear non-Gaussian causal models. You can see why this model can be identified from data uniquely. And then we are going to have a look at the non-stationary functional causal models and see how we can discover causal relations by making use of them. And finally, we will see some extensions, including how to analyze the causality in time series and how to learn hidden causal variables and their relationships, or the hidden causal representations from data. And also, as a special case, we'll see how we can deal with the measurement error in the observed variables. Okay, probably I should just pause for half a minute. Is there any question regarding conditional independence constraint-based methods? Currently, no. Okay, so if there are no question, I will just give me a second. No one raised the hand. Okay, let me just go ahead. Right here, you can see the scatter plot of the data pairs in the Tübingen dataset, Tübingen causal effect pairs dataset. So in the first dataset, we have x1, x2, two variables. We have realizations of values, and this is the scatter plot. Now, if you make use of a conditional independent method, independent-based method, usually you have to make use of at least 3 variables because you want to make use of conditional independent relations. And now we have 2 variables. Can we discover which variable is the cause? With the traditional methods, you cannot, right? So what can we do? Then you can see that we have to assume something about the causal mechanism. And then all of a sudden, a lot of information about the causal mechanism can be discovered from data. By the way, the 2 variable case is the fundamental case in causal discovery. Why? Because if you can find the causal direction and the causal model for 2 variables, then no matter how many variables you are given, you can just condition other variables in the right way, and this will become a 2 variable problem, right? That's why the 2 variable problem is really fundamental. Okay, so here you can see a causal process. Rain causes the wet ground. So we know, oh, when we say this is a causal process, we mean the following thing. If there are no common cause for rain and wet ground, then the generating process of the cause, rain, would be completely irrelevant to the generating process. From rain, the cause, to the effect, wet ground. Right here, that means, oh, the generating process of X and the generating process from X to Y are completely irrelevant. E, the error term, is involved in the second process. That's why X and E, cause and noise, would be independent. Okay, so, and this gives the definition of functional causal model. So we can just represent the effect as a mathematical equation or mathematical function of the direct causes and noise. The noise is the omitted factors, right? We cannot measure everything. And the noise is represented by E. And here, X and E are not are independent. If X and Y do not have other common causes, if there are no common causes, then X and E shouldn't be related in any way. That's why X and E are independent. So this is a functional causal model. This model is very general, right? It's just a functional form. Without any assumption on the functional form, we cannot make use of this representation to discover causal information. X and Y would be symmetric. However, if you introduce some structural constraint on the function f, all of a sudden, you can find that, oh, X and Y are not symmetric. Only one direction between X and Y admits some properties for the causal process. Okay, right here, you can see three typical functional causal models that can be used for causal discovery, because the relationship between X and Y is usually not symmetric according to those models. I mean, if the data were generated by those models. The first one is the linear non-Gaussian cyclic causal model. So effect is a linear function of the causes and the noise. And here we assume not all noise variables are Gaussian. Later you can see the example and how we can solve the problem. The second one is called the nonlinear additive noise model. So right here, the effect is the nonlinear function of the cause plus noise. And the third one is called post-nonlinear causal model. It was first proposed in 2006 to solve some problem in finance. So right here, we have additional distortion function, F2. Later, you will see that, oh, this function is actually very useful. Okay, now let's try to see why we can go from correlation to causation in the linear case. Before that, let's just remember the definition of independence and conditional independence. So when we say X, Y are independent, we mean that the joint distribution or joint distribution function or joint probability density function or mass function can be written as the product of the individual ones. In other words, the conditional distribution is the same as the marginal distribution right here. So what that means? It means X is not relevant, or X has no information about Y, or Y has no information about X. So similarly, if X and Y are conditional independent given Z, then we have independence between X and Y for any value of Z. Okay, this is conditional independence. So now let's have a look at the two examples. Right here, in the first example, you can see the red data points, the scatter plot. First of all, we know that they are uncorrelated, okay? But do you think, remember, the covariance is just the expected value or averaged value product, right? After you center the data. That's why you can see, oh, the average product of this variable and that variable would be 0. And this is right here, this is the origin. So they are uncorrelated, but do you think the two variables are independent? Yes or no? Here, I would like to see your response. So maybe you can, if you think they are independent, please just click on yes. What can I do? Yeah, you can just say yes. And if you think they are not independent, please say no. Okay. George said they are dependent. No, no. Okay, wonderful. Then I will stop. And right here, you can see another example again. So Y is a quadratic function of X. They are uncorrelated, but clearly they are dependent. And then whenever you do regression, linear regression or nonlinear regression, by construction, the regressor is uncorrelated from the regression residual, but they are not necessarily independent, as you can see from this illustration, which we will see in half a minute. So right here, you can see the shape of different probability density functions. This is the Gaussian distribution. All variables have unit variance and zero mean. So this is the Gaussian one, this is Laplace distribution, and this is the uniform distribution. Right here, for the Laplace distribution, you can see the probability distribute the density, the value of the density function is very high for values very close to zero for small values. And also as a consequence, because we have the same variance for the three variables, right here the distribution would be higher. That's why we say it's a fat-tailed distribution. This is Gaussian uniform. And right here you can see the data points drawn from the distribution. You can see how they look like. Okay, now let's try to go from correlation to asymmetry between two variables in the linear case. First of all, let me just generate the data this way. I first generate x, and then I generate y from x. I make use of this process. Y is a linear, y is just a coefficient times x plus independent noise e. In other words, according to this process, x causes y, right? And then the first row shows the Gaussian case, where x and e are both Gaussian, and finally x and y are jointly Gaussian. So this is the scatter plot. And now let's try to explain the effect y with the cause x by linear regression. So we regress y on x. We have the residual, and the residual is uncorrelated from x, and also they are independent. Why? Because we just recover the original noise term, right? And then we regress x and y, the different direction. And we find the residual. Again, they are uncorrelated. And again, they are also independent because in the joint Gaussian case, as long as they are uncorrelated, they are independent, right? That's why the joint Gaussian distribution is very attractive in many cases, because in this case, uncorrelated or zero correlation is equivalent to independence, statistical independence. In the second case, we have non-Gaussian distributions, and in particular, both x, the cause, and e, the error, follow the uniform distribution. And here you can see the scatter plot of x and y. Now we do linear regression. We regress effect y on the cause x. We recover e, they are independent. So the error term would be independent from x. Now we do the same thing in a different direction. We regress x, the cause, on the effect y with linear regression. Now we can see, again, they are uncorrelated by construction. They are uncorrelated. However, they are clearly dependent, right? So for the wrong direction, the regression residual would be dependent on the hypothetical cause of the predictor, as you can see from here. That's why we can discover causal direction between x, y in the linear non-Gaussian case. Because for a wrong causal model, the residual will not be independent from the predictor. However, this is not the case if the data are jointly Gaussian, as you can see from this row. Right here, you can see the super Gaussian case. Again, I generate the y from x this way. However, x and e are both sparse or both fat-tailed. I use the Laplace distributions for x and e. Here you can see the scatter plot of x and e, and this is the scatter plot of x and y right here. And if you do regression, if you regress y on x, you can see you can recover the noise, right? And they are independent. However, if you regress x and y, as you can see from here, the residual, although uncorrelated from y, is clearly dependent on y because the distribution of this variable given the other variable would be sensitive to the value of the second variable. They are not independent. Right here, you can see this is the regression line. It's not here. Why? Because we have a lot of data points here, right? That's why this regression line cannot just go through those data points. It's something between this cluster and this cluster. Okay, so basically you can see intuitively we know that in the linear non-Gaussian case, we can discover the right causal direction. And if you find the causal structure with the right causal direction, then you can estimate the causal parameters. Because if you have the structure and the data, you can just use the regression to find the causal coefficients. So more generally, we have this linear non-Gaussian acyclic causal model in which each variable is a linear function of its parents or direct causes and some independent noise. And in matrix form, we have this. This x is a vector of all variables. X is b times x plus e. And right here, b is called causal adjacency matrix or weighted causal adjacency matrix. So B has a Bij as entries. And we assume the disturbances or noise terms or errors are non-Gaussian, or at most one of them is Gaussian. And clearly we assume they are mutually independent, as we just saw from the assumptions for functional causal models. Probably there are questions. Let me have a look. Okay, I got a question here, so let's just pause for a moment. What's the feature of non-Gaussian distributions that makes them suitable for this inference? Would it work for general elliptic distribution as well? Okay, good. So as long as the distribution, the non-Gaussian, is fine. Later you can see why. Okay, I will give you something probably in 2 or 3 minutes. You will see why and how the Gaussian distribution is so different from the non-Gaussian distributions. And you can see what features in the non-Gaussian distribution can be used to determine some essential information uniquely. Okay, just wait a second. Okay, right here at the bottom, you can see we have a set of equations or structured equation models. Remember definition, right? It's a structured equation model because for each equation, the variable on the left-hand side of the equation is the effect, and those on the right-hand side of the equation are the parents of that variable. And equivalently, we can represent the system with graphical models. Right here, we know all x2 is a direct cause of x3 with the parameter or causal coefficient 0.5. And usually, we don't explicitly give the noise term. Here, I just give the noise term in order to better understand the relationship between the noise terms and the observed variables. Now, the problem is how we can estimate this causal model from data, from observational data for xi's observed variables. In other words, we want to find the B matrix, because if I have the B matrix, that you will see that if I have the B matrix, then I have either this graphical representation or this set of equations. In other words, we have the causal information. And we can make use of a statistical technique known as independent component analysis, ICA. So right here, this is how ICA works. We have a set of observed variables, xi's, x1 to xm. They are assumed to be linear mixtures of some underlying unobserved independent variables, si's. So they are linear mixtures. And this part, everything here, right, is not observable. To recover this hidden system or information of this hidden mixing procedure, we just apply another linear transformation, W. We tune the parameters to make the outputs, yi's, independent or as independent as possible. And then, under some assumptions, we know that the estimated variables are just the estimator of the originally independent variables, si's. So basically, we just estimate those variables by making use of yi's, the outputs of the linear transformation or the demixing procedure. And we know that this is one way to invert the system in some sense. So this is the linear mixing procedure. Observed variables are linear mixtures of the hidden independent variables. And right here, we apply linear transformation to x observed variables, and we find the independent components as components of y. So under two assumptions, we can just recover the original independent variable si's just with some trivial indeterminacies. What assumptions do we need? The first one is that at most one of the independent variables si's is Gaussian, at most one. Later you will see why we have to make this assumption. The second one says that the number of sources is either smaller than or equal to the number of observed variables, sensors. So right here, n is not larger than m. Otherwise, it's called overcomplete. It's more difficult, much more difficult, because you have more variables in the hidden part, but you only have a smaller number of variables that you can observe. Recovering this system is not very easy. But now we assume that's not the case. So under those two assumptions, we can just estimate this A matrix up to the scale and the permutation indeterminacies. What does it mean? First of all, we cannot recover the scale of A because we can always exchange some factor between S and A. It's trivial. In other words, if you just basically exchange some factor between A and S, you will not change the independence between SIs, the independent variables. And the second, we cannot determine the permutation, right? We cannot recover the permutation of SIs because no matter how you permute them, they are always independent. Okay, so this is ICA. And right here, you can see the difference between Gaussian distribution and non-Gaussian distributions. This is ICA procedure. We have this set of set of observed variables, xi's. We have linear transformation. We want to make them independent, the outputs independent, right? And usually, ICA procedure has two steps. First, we do something like whitening. We want to make the outputs uncorrelated from each other, and at the same time, we want each component to have a unit variance. So this is called whitening. After this, we just need to find a rotation or orthogonal transformation to further make the output independent. So the first step is the standard. You can just do EVD or SVD decomposition, and then you can white the data. Now let's try to find a rotation or orthogonal transformation to make the components of Y independent. In the first case, variables are Gaussian. Now you can see no matter how you rotate them, right? No matter how you apply rotation transformation to the variables, they are always independent. Meaning that you cannot recover the underlying mixing, the information of the underlying mixing procedure. However, in the other three cases, we can recover the essential information. In the first case, you can see, although they are uncorrelated, clearly they are not independent. To make them independent, to make the rotated variables independent, we have to do something like this. Or you can go further, right? Then you can just change the sign, or you can just change the order of the two variables, but they are independent. And you have to rotate them this way, either this way or that way. But in any case, you can recover the essential property of the mixing procedure. And in the second case, right here we have a scatter plot, right? A way to visualize the joint distribution of the data of the variables. And in the second case, basically originally the underlying independent variables are uniformly distributed. So you have to rotate the variables this way. And in the third case, one independent variable is Gaussian, is actually uniform, and the other is Gaussian, I think. Right here, you have to rotate the variables this way, then you can make them independent. Now you can see the difference between Gaussian and non-Gaussian distributions, right? The Gaussian distributions is just, the Gaussian distribution very simple. We just need to specify the mean and the variance or the covariance if you have multiple joint Gaussian distribution. It's so simple, it's so smooth that no matter how you rotate the variables, it's just the same thing, as you can see from this illustration. But in the non-Gaussian case, you can really find a relatively unique way to make them independent. If you further rotate them, they will not be independent. Okay, So this is Y, and now you can see a demo of the ICA procedure. Right here, we have two observed variables, x1, x2, and on the right, we have the scatter plot as a way to illustrate or to show the joint distribution of the variables. And then we do the first procedure, we do whitening. Now they are uncorrelated, and each of them has a unit variance. You may wonder that, right? Note that here we have a lot of data points here. That's why although the shape is very strange, actually this variable and that variable are uncorrelated, although you can see a trend. Okay, then we go further. First step, second step, and then now you can see finally we can find the independent components from the two variables. And now you can see they are very simple and they are structured, right? And they are independent. This is how, okay. This is how ICA works. Let's just pause. Question, is it possible, is it always possible to make the transform variables yi independent between each other for general distribution if y is restricted to a linear transformation y equals w times x? So basically the question says that, can we always make the outputs of yi's with a linear transformation independent from each other? So the answer is no, clearly no. As you just said, right? In many cases, suppose you just have uniform distribution within a circle, right? Within a circle, uniform distribution. Now you can see no matter how you apply linear transformation, the variables cannot be independent. The distribution of one variable will be sensitive to the value of the other variable. So the answer is no. That's why in some cases, we have to make use of nonlinear ICA or some nonlinear methods to find disentangled representations. Is that the answer to your question? Okay, great, thank you. So now we just saw how we can do ICA, and then let's see how we can solve the problem of causal discovery by making use of the ICA procedure. Very quickly. So in the first row, you can see the linear non-Gaussian model in the matrix form x equals bx plus e. In other words, e, error term, independent error terms, right, can be written as a linear transformation of x, linear transformation. And there, this is the ICA demixing procedure. We have W. Now you can see, oh, E has independent components, Y has independent components. I minus B, the linear transformation, W the linear transformation. That's why this one, this is the mixing procedure of ICA and this causal model are related. Now the problem is how we can make use of this connection to find the matrix B, because B contains the causal information between the variables xi's. So first, how can we find W? We can do so with ICA, right? We just saw that. Second question, how can we see B matrix from W? How can we analyze the W matrix to obtain B? And this is interesting, and I'm going to give examples to illustrate that. So suppose this is W. Now we just need to do three things to find the B matrix. First, we permute the rows of this matrix to make all diagonal entries non-zero. Right here, you can see, oh, I have to permute the matrix this way, or the rows of the matrix this way, to make sure all diagonal entries are non-zero. And the second is to divide each row by the diagonal entry. And then you can see after that, all entries on the diagonal are just one. And then B, the ultimate, the causal adjacency matrix is just the identity matrix minus this matrix, as you can see from here. And then diagonal entries will be zero. Remember that, oh, I haven't really talked about that. So the B matrix, causal adjacency matrix, right, has zero values on the diagonal. Why? Because this represents self-influence or self-loop. This is the influence of x1 on x1, right? That's why we don't assume there are no self-loop, because this kind of information cannot be recovered from data. So it's just zero. And then we have this causal structure. Accordingly, we have this causal graphical representation. So you can see x The first one says, oh, x1 is not influenced by any observed variables. The second row says that x2 is influenced by x1 with parameter minus 0.5. And the third row says the third variable is influenced by 1 and 2 with parameters minus 0.3 and 0.2 and so on. So now with this example, you can see how we can solve the problem. In particular, because the causal graph is assumed to be acyclic, right here, the solution is unique. So we can just recover the underlying DAG uniquely from data asymptotically, if you have enough data, right? Otherwise, you may have random error and you can make wrong conclusions. And this is a really big step, because previously when we made use of conditional independent relations, we could only end up with the equivalence class. We cannot really find a unique DAG, but now by making use of additional assumptions on the causal mechanisms, including the non-Gaussian distribution, we can just recover the underlying DAG uniquely. Okay, in a minute we are going to have a break, but now let me just finish this part because it's closely connected. Some of you may wonder whether it's really reasonable to assume the variables are non-Gaussian, right? We use Gaussian distributions almost everywhere, partly because the form of the probability density function is very, very simple, partly because of central limit theorem, right? If you have the sum of independent variables and allow the number of independent variables to go to infinity, then you have a Gaussian distribution under very mild assumptions. And partly is because of the very nice property of the Gaussian distribution. If the joint distribution is Gaussian, then conditional distribution is Gaussian, marginal distribution is Gaussian. However, another theorem is actually complementary to central limit theorem, but it was kind of largely overlooked in the literature. It's the Cramer decomposition theorem. It says the following thing: if the sum of any finite independent variables is Gaussian, then each of those variables must be Gaussian. If the sum of, say, 10 independent variables is Gaussian, then all those 10 variables must be Gaussian. In other words, the Gaussian variables are closed. They are in the closed system. If you put anything non-Gaussian there and allow this non-Gaussian variable to interact with other variables, then finally all variables will be non-Gaussian, right? So in this sense, Gaussian distribution is really special. And you can also say that if we have linear world, if the relationships are linear, then the distribution shouldn't be Gaussian, right? Of course, the practical issue is how non-Gaussian they are, how many data points we have to make use of to really discover and make use of the non-Gaussianity of the distribution. Here you can see an application of this method, some extended, some modified version of this method to analyze the Hong Kong stock market. So basically here you can see 14 major companies in Hong Kong, and we analyze the daily returns, right? If you have daily return, the resolution is very low, and the causal relation would seem to be instantaneous without a time delay. So right here, yeah, I'm going to skip this, but basically the information is largely consistent with the background information or domain knowledge in the stock market. Just now you saw how we can estimate linear non-Gaussian models from data. And the solution, if the model assumption holds true, then you have a unique solution, meaning that you have a unique structure, including the parameters, the causal coefficients from data. And right here, now let's try to go further to make it more general. Here you can see the scatter plot of xy, where y is the nonlinear function of x plus e. If this nonlinear function is very simple, it's just kind of piecewise linear. I have this, and then I have that linear function. I have independent noise added to the function. So here, if you try to, if you regress y on x clearly, you can find the independent error term because you just recover this true model, causal model from data. However, if you switch them, x, y, and do regression, if you regress x on y, Now you can see the error distribution will be sensitive to the value of y, as you can see from here, right? So this means, generally speaking, even in the nonlinear case, with the wrong direction, you cannot find the independent error term. Okay, so this is basically something similar to what you observed in the linear non-Gaussian case. More generally, let's have a look at the post-nonlinear causal model. So when we develop this model, we believe that the model itself should be very, very general, so that it can be used to approximate the true generating process. And second of all, we have to guarantee that the causal direction is identifiable. Otherwise, it's not meaningful to make use of the model for causal discovery. So we believe that 3 effects should be considered in the model. So here we have nonlinear effect of the causes, we have noise, and in many cases, we have sensor or measurement distortion. If you want to measure something, right, you have to use instrument, and this will introduce some error. And this is the typical issue, or this is the typical case for biological data and for data in social sciences. And later, so you can see some examples. And this model right now, this is called the post-nonlinear model. This is very general. Even if the noise is not additive, but multiplicative right here, you can see it's a special case. Right? This is nonlinear function, this is a function of f, and this is noise. They are independent, and basically this is just another way to put the multiplicative noise model. So the model is very general. Can we make use of this model to discover causal direction? The answer is yes. But here you can see some evidence, empirical results. We are given data sets. We are given the data pairs for x1 and x2. And right here you can see the scatter plot. If you assume x1 causes x2 and fit the model on the data, you find the nonlinear transformations and you recover the noise term. In this case, they are independent. And then if you switch them, if you assume x2 causes x1 and fit the model, then you can see the estimated noise is not independent from the hypothetical cause, which is x2. Now we say, oh, according to this model, x1 causes x2. Actually, x1 and x2 are the altitude and temperature, yearly mean temperature of more than 300 cities in Germany. So altitude should be a cause of temperature, not the other way around. This is the second one. So here, again, you can see, according to this model, x1 causes x2, because for this direction, we can find an independent error term according to this model. But for the other direction, we cannot. And here, x1 and x2 are the altitude and precipitation, respectively, for the cities. Okay, so you can really find the causal direction, even if the causal model is rather complicated, right? It involves two nonlinear functions. Okay, now I'm going to give some theoretical guarantee. How can we trust the result, right? We just prove the identifiability of the causal direction in the 2-variable case by making use of the proof of contradiction. So given data, suppose the ground truth is x1 causes x2, right? Now we assume that the other direction can also satisfy the post-nonlinear model, and then for the same distribution, right? We assume both of them hold true. We'll find the constraint, which is actually a differential equation, and then we can solve the equation, and finally you can see there are only 5 solutions. In other words, in only those 5 situations, we have the symmetric relationship between the cause and the effect, right? Means that even for the wrong direction, we can find the independent error term. And those cases are actually very specific. The first one is the linear Gaussian case. The function is linear and distribution is Gaussian. So in this case, we know that we cannot find the causal direction between 2 variables because they are symmetric. zero correlation is equivalent to independence. And all of them are very specific. You have to tune the nonlinear functions and distributions very carefully so that one of them is true. So in other words, generally speaking, causal direction is identifiable, even if data were generated according to this very general model. And since linear models and nonlinear additive knowledge model are special cases, this result also applies to the two simpler cases. So in other words, generally speaking, causal direction is identifiable from observational data, even if we have this very general model to generate the data. Okay. Any questions? So far, we just saw how we can make use of linear non-Gaussian causal model and nonlinear causal model to discover causal information. In particular, here, I focus on how to identify the causal direction, because this is the missing part for the previous methods based on conditional independent relations, right? With those methods, you cannot find the direction between two variables. Sometimes you can find the direction because of this structure, right? But generally speaking, you cannot solve the problem in the general case. Now we can, because for any two variables, we can solve the problem. Then no matter how many variables you have, in theory, you can solve the problem. And now let's have a quick look at some extensions of the functional causal models. First problem is very important, very practical. It's a causality time series. So we just focused on a very hard problem, which is how to find the causal information from ID data. What if we have time series? Right? How can we discover causal information from time series? So I just want to give a rather complete introduction to the problem. So here you can see this is traditional work, very classical work, Grandier causal analysis. Right here, Grandier himself said that Grandier causality is not necessarily true causality. That's true. Actually, only under very restrictive assumptions, Grandier causality is true causality. Those assumptions include that there are no confounder and that you have the right resolution for the data. So if you have low resolution of the data compared to the original causal frequency, then you cannot recover the true causality by Grandier causal analysis. Okay, and then you can just view this problem, causal discovery from time series, as a special case of causal discovery from ID data. What does that mean? It means that we can just apply constraint-based methods combined with the temporal constraints, temporal precedence information. Causes happen before the effects, or they can happen at the same time if you have low resolution, but causes cannot happen after the effects. So this is the method used in this paper. And also you can apply the functional causal model like linear non-Gaussian model to the data. And also further, you can apply, you can benefit from temporal constraints, right? So in other words, you can just consider causal discovery from time series as a special case of causal discovery from ID data. And then you can also consider both the time-delayed causal relations and instantaneous causal relations. Right here, as you can see this paper. And you can discover true causal relations at the original causal frequency from low resolution data. Here by low resolution data, I mean you can have subsampled data or temporally aggregated data. Later you'll see the definition. And furthermore, you can recover true causality from partially observed time series. And here you can just see the references. Now I'm going to show two pictures, two slides. One of them is on the connection between Grandier causality and constraint-based methods for causal discovery. So Grandier causality relies on two principles. The first one says that future cannot cause past. The second one says there are no redundant information. So basically says that there are no deterministic relationship. Cause contains unique information about the effect. Then, according to Grandier in this 1980 paper, we say X causes Y if this conditional distribution, given the complete information set, is different from the conditional distribution of y given the information set without knowing x for this moment, right? So what does it mean? If this inequality holds, we say yt plus 1 is conditionally dependent on x given the remaining information, right? So this is just one particular way to find the causality based on conditional independence relations. And furthermore, you know, our causal direction can only go from the past to the future. That's why you can immediately recover the whole model by making use of this condition, this conditional independence condition. In practice, sometimes we have causality mean or linear granular causality. To do so, we can use something like vector autoregression model, right, to capture the causal relations. Okay, so this is how granular causality or granular causal analysis is connected to the conditional independence-based method for causal discovery. And right here, you can see what I mean by the two schemes of temporal of deriving low-resolution data from high-frequency data. So in many cases, causal relations can happen very, very quickly, right? Like in stock market, if company A causes company B, then the causal inference will take place within 1 minute and 20 seconds. Usually this is the case, but very often time we just analyze low-resolution data set, daily returns, right? So the first scheme is called subsampling. Right here, we can see we have the original high-frequency time series, and then we only keep one of them, right? This one, x1, and then xk plus 1 and x2k plus 1. So we just keep one of them every every k consecutive data points. We only keep one. This is called subsampling. And right here, you can see the graphical illustration of this procedure. We have the original causal process time series, and then we cannot observe the information in between, right? Between this observed value and that observed value. And now you can see, not surprisingly, if the k downsampling factor is very large, then you have a lot of missing information. And finally, causal information tend to disappear, right? So suppose this guy calls that guy, and every time, right, you have the causal relationship, and suppose you just miss a lot of values in between, and finally, the first one and the last one will seem to be independent. This is the subsampling, and the second one is the aggregation, temporal aggregation. So you just take the sum of the k consecutive data points. And this is in practice, very often we have this issue, right? The daily return, stock return, is actually the sum of the short-term log returns. And in this case, it's very nice to see the following thing. As you increase the aggregation factor k, the causal relations are still there, right? As you can see from this equation, if you compare the original causal process represented by this vector autoregression model and this model, you can see, oh, I still have the same A. However, I do not have time delay. So time delayed causal relations will look instantaneous. So that's and also at the same time, we cannot recover the information of self-loop. And if you have finite k, we can recover the original causal information or true causal information from data. And if you want to make use of the method, or if you want to go further in this line of research, you can have a look at those papers. Okay. To give examples, for instance, GDP is aggregated data. fMRI signals are usually aggregated data. Stock returns are aggregated data. Temperature data are just a subsample data. Okay. And now let's have a look at how we can deal with the confounders. So first, suppose we don't care about the confounder, we just care about the causal relations between observed variables, right? So FCI provides a way to recover some information, but it's not really complete, because whenever it's possible to have a confounder, you have to indicate that. So right here, by making use of overcomplete ICA, we can recover the structure of the observed variables, even if they are confounders. And under some further assumptions, as you can see from this paper, we can even uniquely identify the causal parameters, causal coefficients, represented by A3 here. Here, we have to use overcomplete ICA because, as you can see from this example, we observe two variables, but actually there are effects of three independent variables: this noise term, and this confounder. That's why it's called overcomplete ICA. Okay, so we can say something, but right here we have no idea about the relationships among the latent variables. However, in many cases, the measured variables, like image pixels, are just reflections of the underlying meaningful causal variables, hidden variables, which are causally related. And then, if you want to understand the system, you want to discover the hidden variables as well as their relationships. How can we solve the problem? And this problem is sometimes known as hidden causal representation learning, or discovery of hidden causal representations. In the linear Gaussian case, one can make use of the tetrad condition to solve the problem, as you can see from this very nice paper. And you can go further. In the linear non-Gaussian case, we just need to make rather weak assumptions regarding the structure, and we can go further. For instance, if you make use of the triad condition given in this paper, in this case, you can recover not only this structure, but also the causal structure, including directions for the latent variables. So you can recover not only where the latent variables are, but also how the latent variables are causally related uniquely. Of course, here we are considering linear models. And so far, I don't think there's any kind of convincing work on how to discover the hidden world, hidden variables and their causal relations in nonlinear cases. This problem is very important, but you have to do the work. Last issue I want to mention as the extension of causal analysis based on functional causal models is how to deal with measurement error. In many cases, we have measurement error, right? If you use the instrument to measure something, this process can introduce error. And in some cases, we don't even have a very good way to measure the variable. For instance, if you want to see the regional safety, right, of a particular country, a particular area, what can you do, right? You have to make use of some other variable, like the number of crimes per day or number of crimes per month as a surrogate for that variable. Then inevitably, you are going to have measurement error. The measurement error is the error in the observed variable relative to the underlying hidden variable you are really interested in. Here you can see a graphical representation. So here xi tilde are the hidden true variables we want to analyze. And unfortunately, we have measurement error, right? We observe xi's, they contain measurement errors. First of all, the conditional independent relations between the observed variables can be very different from the true variables, from those relationships between the true variables. That means we have to do some adaptation to recover the true causal structure for the noise-free variables. And even if you apply functional causal model-based methods, you suffer from the same problem because even if this guy calls that guy, so x2 tilde calls x1, now because of measurement error, even if you consider the relationship between x2 and x1, right, in the right direction, you don't have independent error term. But we just studied this problem, and the conclusion is as follows. Under rather mild assumptions, we can still recover the essential information of the underlying true graph over the measurement error-free variables. So, and we propose some method to solve the problem. Again, we assume linearity. If you consider nonlinear models, probably you can do something. And that's very important because we often have nonlinear relationships in practice. Okay, to summarize, right here, first of all, we know that conditional independent based method or constraint based method often end up with equivalence classes. So we want to go beyond that to recover the underlying DAG uniquely. How can we do so? We can just make use of some rather mild or strong assumptions also on the causal mechanisms. So if you assume the data is a linear non-Gaussian, then we can recover the underlying model uniquely. And if you know that the procedure is nonlinear, then usually we can recover the underlying causal DAG uniquely again. And in practice, there are so many issues to address, right? And just now, you just saw how we can deal with hidden variables and their causal relations in memory error, and how you can discover causal information from time series. Of course, there are so many open problems in causality, especially in causal discovery. So you can easily find some problem to work on. Okay, so let's take a 20-second break. Is there any question? I know it's very fast, but maybe you want to have a look at the slides later. And in particular, if you are interested in a specific topic, just find a reference.
And we have also gathered some questions that we can answer at the end.
Oh, or maybe if you already have a question, can we just answer the question right now?
We can answer questions right now. Yes, sure. Let me.
Yeah, because otherwise, if you get probably there, yeah, some of them will forget the question.
So connected to now, so the presentation on Granger causality. So we discussed causality in time series, but what about causality for sequences? For example, event data or even NLP. Can the same techniques be applied?
Sorry, I missed the last sentence.
Yes, so if the same techniques, for example, Granger causality or the general techniques that we have seen today and yesterday, can be applied for sequences, not only time series, for example, event data or NLP.
Yeah, yes, a very good one. First of all, I think, yeah, you can, because I just talked about the general principles. And furthermore, if you have other kind of data, sequential data or structured data, you can go further. You can make use of the structural information in the data. So answer is, first of all, yes. Second of all, probably you can go further by making use of the specific property of the data you have.
Great. And also another question is that there have been recently approaches using deep learning for causal discovery, for example, from the Benjos group. We have not discussed them here. What are your thoughts on them?
Okay, that's a very good question. So you can always design methods to solve the problem, but the most important thing is to really find a principle based on which you can solve the problem, right? For instance, right here, for causal discovery from non-stationary or heterogeneous data, I presented the basic work based on conditional independent relations. Okay, let me quickly go back. And Benjo and his group did something, right? It's a method, but basically they use something like a quick adaptation as a criterion, right, to find the causal representation. Actually, here we just use the conditional independence, and as you can see from this result, from this framework, conditional independence is a principled way to do causal discovery. And of course, in practice, you can use some other criteria to achieve something similar, right? They are related. And that's why I didn't talk about that specific method, because we have to wait to see whether the principle is really a good one for causal discovery from non-stationary or from data with the distribution shift. So, but if you are interested, we can have a discussion later. Okay.
Mm-hmm. Mm-hmm. And another question is on if it is possible to do causality in general without the do calculus.
Okay. We use the do calculus to use causality, right? No, there are different interpretations of the results. First, classical way to find the causality is to use interventions, right? We intervene on something and then see the effect, then we can find the causality. So from this perspective, yes, with the Duke calculus, by which I suppose you mean interventions, then we can find the causality. Second, right now I'm talking about the causal discovery, in which we just make use of observational data without any intervention, and we aim to discover true causal information. And third, if you know the causal model, in particular, if you have the causal structure and observational data, then you can just identify causal effects, which involve the causal effects involves the Duke calculus. You will see this in probably 3 or 4 minutes. So basically, I just try to give my answers according to my understanding of the question. If it's not clear, or if it's not what you mean, maybe you can just go further. You can just ask questions. Thank you.
Then another question is that there are many names for the field in publications, for example, causality, causal discovery, causal inference, causal structures. Where do you draw the difference? Are there any differences?
Very good one, very good one. So I tried to, you can see, I always distinguish between those terms. Here by causality, I mean, basically causality is just a field, right? As long as you care about the causality, you say the causality research. And then I use the term causal discovery. By causal discovery, I mean finding causal information like a causal structure or causal model from non-experimental or observational data. So you don't do interventions, you want to discover causal information. This task is known as causal discovery. The third one is the causal inference or identification of causal effects. So right here, you will see this. I will define this problem in a few minutes. Basically, this problem is very different from causal discovery because causal inference or identification of causal effects assumes that we have a causal structure and then qualitative causal structure, and then you want to estimate the quantitative strength. You want to see how X influences Y, right? You want to see whether this influence is really significant and so on, or very heavy and so on. So they are very different. And structure learning, so causal structure learning is the same as the causal discovery because you want to discover causal information. And in contrast, we also have Bayesian network learning, right? Bayesian network learning is also a kind of very huge, it also has a very huge community. Bayesian network learning is different from causal discovery because if you want to learn a Bayesian network, you don't care about whether this Bayesian network is really causal, right? For instance, if you have two variables which are dependent, then you don't care about the direction if you just want to end up with a Bayesian network. However, if you care about causality, you have to find a direction. You have to make sure this direction is causal, right? So, however, Bayesian network you learn that you can learn from data is related to causal representation. Why? This is why just now you can see that with the conditional independent Bayesian method, we just end up with the equivalence class in which usually we don't have a unique DAG, right? This is because you can, if you just learn Bayesian network from data, then you can always convert the learned Bayesian network to an equivalence class, and then you can trust it. By trusted, I mean the following thing. If the age is directed, you can trust that, oh, this guy is the cause of that guy. If the age is undirected, right? Then you say, oh, I don't know the causal direction. But if you just view that as a Bayesian network, the direction can go either way. Now, from the causal perspective, as a causal representation, you cannot do so. If you cannot determine it, you just say, I don't know, represented by undirected age. So I hope this just clarifies the differences between different concepts.
So another question, so more general one, is if there are success stories in machine learning using causal methods.
Yeah. Oh, let's see whether we have time for that. Yes, that's true. Clearly, in many cases, we care about the causality, even if we want to do machine learning. I will try to give examples and some tasks at the end of the talk. Okay. And in case you don't get the answer you want, please email me or just stay here after the tutorial. Okay. Anything else?
Yeah, so last one is that causal inference and reinforcement learning, they seem to have similar objectives. Where do you see the differences between both fields? Where do they complement each other?
Which fields?
Reinforcement learning and causal inference.
I see. Reinforcement learning and causal inference. That's a very good one. First of all, if you do reinforcement learning, most of the time, right, you have causal information. By default, you make use of causal information, right? You do this, you know that our action will change the state. Action will lead to some reward and so on. So from this perspective, a lot of people in reinforcement learning believe they are making use of causal information, right? However, at the same time, probably in some cases, you need to make use of the properties of causal system more rigorously. So in other words, even if you do reinforcement learning, it is possible that you can formalize the intuition you use to solve the problem by making use of concepts and methods in causality. And this way, maybe you can solve complex problems in an easy way. For instance, probably you can deal with the confounders or changing environments or other problems in a more principled manner. Okay.
Great.
Yeah, in case you are not happy with the answers, please indicate that. Okay. Thank you. Now we don't have much time, so let's go to next part. Because
yes.
Some questions are related to next part. So last part. Come on. Yeah, I'm waiting. Okay. So in this part, you see how we can identify causal effects. This is one of the questions I just received. So you can see what we mean by identifiability of causal effects, and you can see how we can estimate them very briefly. And also you can see the definition of propensity score and why it's useful for identification of causal effects or causal inference. And then you see a very quick look at the relationship between causality and machine learning. If time permits, I will share some general thoughts, and also we'll have a look at causal ways of doing domain adaptation. Remember, we have 3 questions to answer in AI. The first one is sometimes called conditioning. The second one is sometimes called manipulation, and the last one is counterfactual. Clearly, for the last 2, we care about the causal relationship. And the second one is what I'm going to talk about right now. We want to see the effect of interventions. So it's about identification of causal effects. So here you can see I have a probability distribution of recovery, this variable, given intervention on treatment. So this is known as the causal effect of treatment on recovery. Okay, how can we find it? So the golden standard is to make use of randomized controlled experiments. So here, in this case, you have 2 groups. One is a control group, the other is a experiment group or treatment group. And then you have to make sure that all the other relevant features either have the same value across 2 groups, or you have to make sure that those features are completely random, following the same distribution across the 2 groups. And then, given that all the other features either have the same value or the same distribution, if you observe a difference in recovery, then this difference must be caused by treatment. In other words, you are sure there is a causal relation from treatment to recovery, and also you can estimate it from data. You can estimate how strong it is from data. However, these kind of experiments are very expensive. And in many cases, it's not possible to do the experiments. For instance, in social sciences, right, you cannot force people to divorce, right? So many things are prohibited. What can we do? However, we can just collect data, we can observe data, right? And here you can see an example regarding how we can solve the problem. Remember this example, Simpson paradox. We have a common cause, stone size. We want to see the effect of treatment on recovery. So if you care about this, if you look at this row right here, essentially this row is implied by the dependence pattern, or in particular conditional distribution of recovery given treatment. How can you calculate the conditional distribution? Basically, you make use of this equation, right? Right here, you have distribution. You have to marginalize out S, stone size, and you have to make use of conditional distribution of stone size given treatment, right here. This is just an application of the chain rule and the sum rule. And if you want to find the causal effect represented by the probability distribution of recovery given treatment, given intervention on treatment, we have to do this. Remember the definition of intervention. You have to cut this guy off, because when you do intervention, you don't make use of the original mechanism for this variable. You just set the value to some specific one, say A or B, right? In other words, when you do that, when you do intervention, the conditional probability distribution of stone size given treatment would be the marginal distribution of stone size without condition on treatment, because after you do intervention, S and T, stone size and treatment are independent. Now, this is the equation you can make use of to find the causal effect of treatment on recovery. Okay, and those two equations just show the difference between conditioning and manipulating. You basically do manipulation or intervention on this variable treatment. Now let me try to give a graphical illustration on the difference. Here, right here, I have patients with small stones. Those patients receive treatment A, those receive treatment B, and the y-axis is the recovery success rate or recovery rate. And the size of the circle indicates how many people with stone size receive different treatments. So a small number of them receive the A, and a large number of them receive the B. And the same thing happened to patients with large stones. A lot of them receive A, and only a small number receive the B. Now, if you do conditioning, essentially you just use this way. You just marginalize out S according to this equation. You just average the success rate with this weight. And this weight is sensitive to treatment. And right here you can see, oh, here I have a lot of people. That's why the average, the value would be close to this value. And for B, here I have a lot of people. That's why the average, the value would be close to this value. And now you can see, according to the conditional distribution or the mean of success rate, or B seems to be better, right? But this makes no sense if you want to give a recommendation, because it's not causal. In contrast, if you consider this conditional distribution are given intervention on T, this is just a way to measure causal effects. Now you can see we have PS as a weight when you integrate out S, or when you sum over S. In other words, when you take the average of this value and that value, and when you take the average of this value and that value, you just use the same weight. This weight is not sensitive to treatment anymore. And then you can see, oh, you will see the same trend. Now I see, according to this measure, A is better than B, right? So this is the difference between conditioning and manipulating. Okay, formally, what do I mean by identifiability of causal effects? First of all, we know this is a representation of a causal effect, distribution Y given intervention on X to X. And then remember the setting. We have two things. First of all, we have a structure. Structure is given. Second, we have data. we have data for only a subset of the variables. Right here in this example, suppose we only observe treatment and recovery. Suppose this guy is hidden. Now we can see we are given the structure, we know, oh, there is a common cause which is not observable, and we have data for those two variables. Now, the question of whether the cause effect represented by this guy is identifiable is defined this way. We want to see whether two different causal models with the same causal structure and the same distribution for the observed variables will always give the same causal effect. Clearly, if all variables, all relevant variables are observable, then it's always identifiable. But if you have this hidden variable, remember in the symmetry paradox, now if this guy is hidden or confounder, then this effect is not identifiable because we cannot determine the property of this causal link from their distributions, right? Due to the confounder. Okay, so I hope this is clear. Giving lecture on Zoom is really annoying because I cannot see your face, I cannot see your feedback, but I hope it's clear to you. And now, Professor Rubin from Harvard developed a potential outcome framework regarding whether we can identify causal effects. And Pearl, and also Peter Sberti at CMU, Pearl at UCLA, developed the graphical representations of the conditions. So here you can see the backdoor criterion is a graphical criterion, a specific criterion that can be used to determine whether the causal effect of X on Y, some variables, is identifiable. So first, let's have a look at the backdoor. Probably I cannot give details. I will just explain what is relevant in this particular line of research, and then we'll have a quick look at why we care about causality when we do machine learning. So basically, backdoor criterion is, I should put it this way. Suppose a set of variables satisfy backdoor criterion, and then the causal effect will be identifiable. So if Z satisfies backdoor criterion relative to X, Y, ordered pair, then the causal effect of X and Y is identifiable by making use of this formula. And this is the front door criterion. Now you can see Z is not there, it's not on the back, it's not in front of back door, it's in front of front door relative to Y. And this is the front door criterion. So even if you have a confounder here for X, Y, because of this variable Z satisfying front door criterion, the causal effect of X and Y is identifiable by making use of this formula. And here you can see application. So even if you have a confounder, we can still identify the effect of smoking on lung cancer because of the additional variable Z, the tar. Okay. Remember structure equation models. So here for simplicity, now I'm going to define potential outcome framework, but I'm going to define potential outcome and counterfactual variable. So for simplicity, suppose we have only two variables, X and Y. And right here, you can see the structure equation models. X is determined by something that is not in the system, and Y is determined by X and some noise, right? X causes Y. So, and we also have U. U is a particular experimental unit, say a person. And then for each unit, we have the value for EX and EY, say small EX and small EY. And then, now suppose we do intervention on X. We just set the value of X to small x. And accordingly, right, this is the first equation. And also the second equation will become this one because the variable X will become a small value of X. Okay, now potential outcome is this guy. It's the value of Y given by this equation for unit U. If you are given unit U, then you have a specific value for this EY, right? So this is the definition of potential outcome. Now you can see if you have multiple values for X, 0 and 1, treatment control, right? Then at least one of them, at least for one of them, the potential outcome is not directly observable. Why? Because for a particular unit, for any unit, you can only do one particular intervention, right? You can intervene to set the value to 0, and then the potential outcome corresponding to value 1 is not observable. So, and sometimes we can also write potential outcome this way. So this is just a value of y, given intervention on x to set the value of x to small x for the unit u. If you just drop u here, then this is a variable because ey is random. Now this is called a counterfactual variable. And you can understand this variable as a description of the causal mechanism from x to y, because here x is fixed, right? You do intervention. You don't care about how x was generated. You only care about this mechanism. So this counterfactual variable represents the mechanism from x to y, or the mechanism to determine y by making use of the cause x. Then you can see the connection between the graphical criterion and the criterion in potential outcome framework. For instance, the backdoor criterion can be understood this way. So I'll skip this. Basically, it's related to conditional ignorability. They are equivalent. And there's also a unification of the criterion of the graphical criteria for identifiability for causal effects. Basically, a sufficient condition for identifying the causal effect from x to y is that there exists no bidirected path between x and any of its children. Here, by bidirected path, I mean a path with only bidirected edges. And by bidirected edge, I mean a confounder. So here is a bidirected edge. It just means that there's a confounder for x and y. Some C here as a common cause, direct common cause of x and y. And also there exists a necessary and sufficient condition. You can refer to this paper, but basically you can quickly check whether the causal effect of x and y is identifiable by making use of the graphical representations. Okay, so I skip this. You can just verify that. And one thing I want to mention is that the previous conditions apply non-parametrically. We don't have any parametric assumption. If you have parametric assumptions and linear models, then you can further refine the conditions. So in this case, if it's non-parametric, then the causal effect of x and y is not identifiable. But if linear, then it's identifiable. And causal effect is represented by alpha, the coefficient again. So one last thing regarding identification of causal effect is the propensity score. Suppose we want to identify, we want to see the average causal effect of x and y. So we have to do this, right? This is the distribution of y. This is the causal effect of x and y. We have to sum over C according to the probability distribution of C, right? So if the two groups with different value of x have the same distribution PC, then it's easy. However, in many cases, we don't have that. If you have that, you are doing randomized controlled experiments. So distribution of C can be different across groups. How can we solve that problem? So we can either match the distribution of C, right? Usually it's very difficult because C can be very high dimensional. So one way to avoid that problem is to use the propensity score. Propensity score is defined this way. It's just a conditional distribution of x equal to 1 given the covariance, given all variables in C. Since C is a random variable, this is a random variable. However, this random variable is just a single random variable. It's not a random vector, it's a single random variable. Because this condition, because this property, which says x is independent from C, given the propensity score, we have the following result. So this causal effect right here can be rewritten in terms of H, the propensity score. Propensity score is just a single random variable. C can be a high dimensional vector. That's why this guy is easier to calculate in most cases. And that's why we can, in many cases, we really benefit from this propensity score. Remember, propensity score is a function of C and it's a random variable, but it's simple. Okay. And finally, I think we can either stop here or maybe you can stay here for another 3 minutes. We will stop. I will stop in 3 minutes. First of all, at the beginning, I gave some examples, some problems in machine learning. How can we solve the problem? Essentially, you can see the essential problem is our decision process is different from machine decision process. How can we enable the machines to think in our way? Essentially, the machines must find a way to derive the hidden representation of the external world, right? We do so. We see different things. We want to find a unified view to explain all of them. This way, we can see the connection between different scenarios, and also we can see not only the connection, but we can also generalize our representations, and we can also automatically fill in missing information and so on. So the essential step is how we can build this hidden deep causal structure, right? By analyzing only the observed variables. A first method is factor analysis. Does not work here. And you can use the tetrad condition in the linear Gaussian case, and you can also use the triad condition and others in the linear non-Gaussian cases, and you can discover size structure from distribution changes. Regarding this, I think several groups are right now working on the problem. And if you solve the problem, then you can do unsupervised deep learning because you can derive those hidden concepts using disentanglement, right? The disentangled factors can be either the underlying noise terms or external input or the hidden representations. And you can deal with adversarial tech. Why? Because now the machines make use of the hidden features to make a decision, right? Instead of directly making use of the observed variables to make a decision. And this way, because you can encode the connection between different scenarios, it's easier to achieve the so-called artificial general intelligence. And regarding domain adaptation, I don't have time to talk about detail, but I just want to give you a simple illustration. Why we care about the causality, even if our goal is to do machine learning. However, if you do machine learning in the ID case, you can forget about causality. But in many cases, we have distribution shift, right? We have different variable set, we have different sets of variables, and so on. Then we have to care about the causality. So suppose this is me. Right here, you can see my figure and you can see my shadow. Problem one. Suppose you see my shadow. Can you say anything about my figure? According to your experience, you can say something, right? And you can even know that the light is from there. Okay. In contrast, suppose you see my figure, and suppose this is the new environment. You have no idea where the light is from. From my figure, can you say anything about my shadow? Regarding how long it is and in which direction it is and so on? You have no idea, right? So basically here the causal direction is from figure to shadow. Essentially it says the following thing: recovering cause from effects is simple. However, predicting effects from causes can be very difficult in these non-stationary environments. And fortunately, in machine learning, in most situations, the cause is actually the variable we want to estimate, right? Like in this example, the digit you want to write down, the label is actually the cause of the digit you actually write down. And here, the disease is actually the cause of the symptoms, right? So you want to recover them. And you have cause here, that's why you can easily do domain adaptation. In light of that intuition, right? We can easily recover cause from effects, even if the environment is changing. The applications, and right here you can see what we should transfer in transfer learning. Essentially, we care about the causal mechanisms. In particular, we care about the invariant causal mechanisms. And right here, the take-home message is that follows: causality is useful in transfer learning. However, it's not really needed, it's not really necessary, because finding causal model can be much harder than transfer learning. As long as you have a way to discover the property of changes of the joint distribution, you can do transfer learning. So this inspires this way, automated transfer learning. So you have data set, right, different domains, and you can find a graphical representation to represent the changeability of the distribution regarding where the changes can happen, and right, and which modules are invariant, and then you can do adaptation. Adaptation can be understood as the following task. In the new domain, we have values for the features and we want to infer the value of y. So this is nothing but a problem of inference on graphical models. So this is just the end-to-end way to do a domain adaptation if you have multiple domains. Okay, to summarize, in this tutorial, I hope that I just made it clear why we care about the causality, what we can benefit from causality, and how we can learn causality. Regarding how we can learn causality, essentially we can make use of different types of independence. With the conditional independence, we have the constraint-based methods. They are very general because they only rely on conditional independent relations. And with the independent noise condition, we can further find the causal asymmetry between two variables. As a consequence, we can even recover the whole DAG from observational data. And along this line of research, my colleagues in Germany and also some friends in Japan did a lot of work. And the last thing is to make use of independent changes. Essentially, if you have distribution shift, you can further make use of this property to discover causal information very easily. And you also had a very quick look at the identifiability and the identification of causal effects. And finally, the remark is, even if you just want to do machine learning and data analysis, if the environment is complex, then usually you can benefit from causal modeling, because the causal models can allow us to go beyond the observed data, right? To have something very general, very fundamental that can be used to generalize. Okay, thank you very much.